Network Working Group Request for Comments 2083, Category Informational, T. Boutell, et.al.boutell.com, Incorporated. March 1997, PNG Portable Network Graphics, Specification version 1.0. Status of this memo. This memo provides information for the Internet community. This memo does not specify an Internet standard of any kind. Distribution of this memo is unlimited. IESG note. The IESG takes no position on the validity of any intellectual property rights statements contained in this document. Abstract. This document describes PNG, Portable Network Graphics, an extensible file format for the lossless, portable, well-compressed storage of raster images. PNG provides a patent-free replacement for GIF and can also replace many common uses of TIFF. Indexed color, grayscale, and true color images are supported, plus an optional alpha channel. Sample depths range from 1 to 16 bits. PNG is designed to work well in online viewing applications, such as the World Wide Web, so it is fully streamable with a progressive display option. PNG is robust, providing both full file integrity checking and simple detection of common transmission errors. Also, PNG can store gamma and chromacity data for improved color matching on heterogeneous platforms. This specification defines the Internet media type image/PNG, so that would be the MIME type. Table of contents. 1. Introduction, page 4. 2. Data representation, page 5. 2.1. Integers and byte order, page 5. 2.2. Color values, page 6. 2.3. Image layout, page 6. 2.4. Alpha channel, page 7. 2.5. Filtering, page 8. I'm pretty sure these are pages. Yeah, they're pages. 2.6. Interlaced data order, page 8. 2.7. Gamma correction. 2.8 text strings, page 10, 3 file structure, page 11, 3.1 PNG file structure, page 11, 3.2 chunk layout, page 11, 3.3 chunk naming conventions, page 12, 3.4 CRC algorithm, page 15, 4 chunk specifications, page 15, 4.1 critical chunks, page 15. 4.1.1 IHDR image header, page 15, 4.1.2 PLTE palette, that is page 17, 4.1.3 IDAT image data, page 18, 4.1.4 iEnd image trailer, page 19, 4.2 ancillary chunks, page 19, 4.2.1 BKGD background color, page 19, 4.2.2 CHRM primary chromacities and white point, page 20, 4.2.3 gamma image gamma, page 21, 4.2.4 HIST image histogram, page 21, 4.2.5 PHYS physical pixel dimensions, page 22, 4.2.6 S-bit significant bits, page 22, 4.2.7 TEXT textual data, page 24, 4.2.8 time, TIME, image last modification time, page 25, 4.2.9 TRNS transparency, page 26, 4.2.10 ZTXT compressed textual data, page 27, 4.3 summary of standard chunks, 4.4 additional chunk types. Oh, and those are pages 28 and 29 respectively. 5. Deflate/inflate compression, page 29. 6. Filter algorithms, page 31. 6.1 filter types, page 31. 6.2 filter type 0, none, page 32. 6.3 filter type 1 sub, page 33. 6.4 filter type 2 up, page 33. 6.5 filter type 3 average, page 34. And 6.6 filter type 4 paeth, page 35. I don't know if I'm pronouncing that correctly. It is PAETH, and it's kind of a interesting average-like algorithm from what I have observed. 7. Chunk ordering rules, page 36. 7.1 Behavior of PNG editors, page 37. 7.2 Ordering of ancillary chunks, page 38. 7.3, ordering of critical chunks, page 38 as well. Section 8, miscellaneous topics, page 39, or that might be a chapter 8. 8.1, file name extension, page 39. 8.2, internet media type, page 39. 8.3, Macintosh file layout, page 39. 8.4, multiple image extension, page 39. 8.5, security considerations, and that is page 40. 9, recommendations for encoders, page 41. 9.1, sample depth scaling, 41. 9.2, encoder gamma handling, page 42. 9.3, encoder color handling, page 45. 9.4, alpha channel creation, page 47. 9.5, suggested palettes, page 48. 9.6, filter selection, page 49. 9.7, text chunk processing, page 49. 9.8, use of private chunks, page 50. 9.9, private type and method codes, page 51. 10, recommendations for decoders, page 51. 10.1, error checking, page 52. 10.2, pixel dimensions, page 52. 10.3, true color image handling, page 52. 10.4, sample depth rescaling, page 53. 10.5, decoder gamma handling, page 54. 10.6, decoder color handling, page 56. 10.7, background color, page 57. 10.8, alpha channel processing, page 58. 10.9, progressive display, page 62. 10.10, suggestive palette and histogram usage, page 63. 10.11, text chunk processing, page 64. 11, glossary, page 65. 12, appendix, rationale, page 69. 12.1, why a new file format, page 69. 12.2, why these features, page 70. 12.3, why not these features, page 70. 12.4, why not use format X, page 72. 12.5, byte order, page 73. 12.6, interlacing, page 73. 12.7, why gamma, page 73. 12.8, non-premultiplied alpha, page 75. 12.9, filtering, page 75. 12.10, text strings, page 76. 12.11, PNG file signature, page 77. 12.12, chunk layout, page 77. 12.13, chunk naming conventions, page 78. 12.14, palette histograms, page 80. 13, appendix, gamma tutorial, page 81. 14, appendix color tutorial, page 89. 15, appendix sample CRC code, page 94. That could be good to put in my unit test codes later. 16, appendix online resources, page 96. 17, appendix revision history, page 96. 18, references, page 97. 19, credits, page 100. RFC-2083, Introduction. The PNG format provides a portable, legally unencumbered, well-compressed, well-specified standard for lossless bitmapped image files. Although the initial motivation for developing PNG was to replace GIF, the design provides some useful new features not available in GIF with minimal cost to developers. GIF features retained in PNG include bullet point indexed color images of up to 256 colors. Bullet point streamability, files can be read and written serially, thus allowing the file format to be used as a communications protocol for on-the-fly generation and display of images. Bullet point progressive display, a suitably prepared image file can be displayed as it is received over a communications link, yielding a low-resolution image very quickly, followed by a gradual improvement of detail. That is the, what do they call that? The Atom 7 interlacing. Interlacing is what they're talking about there. Bullet point, transparency. Portion of the image can be marked as transparent, creating the effect of a non-rectangular image. Bullet point, ancillary information. Textual comments and other data can be stored within the image file. Bullet point complete hardware and platform independence. Bullet point effective 100% lossless compression. Important new features of PNG not available in GIF include bullet point, true color images of up to 48 bits per pixel. That would be 4-byte color, ARGB or RGBA, I'm not sure. Bullet point, grayscale images of up to 16 bits per pixel. Bullet point, full alpha channel, general transparency masks. Bullet point, image gamma information, which supports automatic display of images with correct brightness/contrast, regardless of the machines used to originate and display the image. Bullet point, straightforward detection of file corruption, and bullet point, faster initial presentation of the progressive display. I butchered that sentence. Bullet point, faster initial presentation in progressive display mode. PNG is designed to be bullet point, simple and portable. Developers should be able to implement PNG easily. Bullet point, legally unencumbered. To the best knowledge of the PNG authors, no algorithms under legal challenge are used. Some considerable effort has been spent to verify this. Bullet point, well compressed. Both index color and true color images are compressed as effectively as in any other widely used lossless format, and in most cases more effectively. RFC-2083. Portable Network Graphics, March 1997. Bullet point interchangeable. Any standard conforming PNG decoder must read all conforming PNG files. Bullet point flexible. The format allows for future extensions and private add-ons without compromising interchangeability of basic PNG. Robust. The design supports full file integrity, checking as well as simple, quick detection of common transmission errors. And by the way, we're on page 4. My mistake. This is page 5 right now. Okay, so let's go down to the next paragraph. The main part of the specification gives the definition of a file format and recommendations for encoder and decoder behavior. An appendix gives the rationale for many design decisions. Although the rationale is not part of the formal specification, reading it can help implementers understand the design. Cross-references in the main text point to relevant parts of the rationale. Additionally, appendices, also not part of the formal specification, provide tutorials on gamma and color theory, as well as other supporting material. In this specification, the word must indicates a mandatory requirement, while should indicates recommended behavior. See rationale. Why a new file format? Section 12.1. Why these features? Section 12.2. Why not these features? Section 12.3. Why not use format X? Section 12.4. Pronunciation. PNG is pronounced ping. 2. Data representation. This chapter discusses basic data representations used in PNG files, as well as the expected representation of the image data. 2.1. Integers and byte order. All integers that require more than 1 byte must be in network byte order. The most significant byte comes first, then the less significant byte in descending order of significance. MSB, LSB for 2-byte integers, B3, B2, B1, B0 for 4-byte integers. The highest bit, value 128, of a byte is numbered bit 7. The lowest bit, value 1, is numbered bit 0. Values are unsigned unless otherwise noted. Values explicitly noted as signed are represented in 2's complement notation. See rationale, byte order, section 12.5. 2.2, color values. This is RFC-2083, page 6, I believe. Yes, page 6. 2.2, color values. Color values can be represented by either grayscale or RGB, red, green, blue sample data. Grayscale data represents luminance, RGB data represents calibrated color information if the CHRM chunk is present, or uncalibrated device-dependent color if CHRM is absent. All color values range from 0, representing black, to most intense at the maximum value for the sample depth. Note that the maximum value at a given sample depth is 2 to the power of sample depth minus 1, not 2 to the power of sample depth. right? Because you have to remember that 0 is one of the values. So it's 0 to 255, not 0 to 256. Sample values are not necessarily linear. The gamma chunk specifies the gamma characteristics of the source device, and viewers are strongly encouraged to compensate properly. See Gamma Corrections, section 2.7. Source data with a precision not directly supported in PNG, for example 5-bit / sample true color, must be scaled up to the next higher supported bit depth. This scaling is reversible with no loss of data, and it reduces the number of cases that decoders have to cope with. See Recommendations for Encoders, Sample Depth Scaling, section 9.1, and Recommendations for Decoders, Sample Depth Rescaling, section 10.4. 2.3 Image Layout. Conceptually, a PNG image is a rectangular pixel array with pixels appearing left to right within each scanline, and scanlines appearing top to bottom. For progressive display purposes, the data may actually be transmitted in a different order. See Interlaced Data Order, section 2.6. The size of each pixel is determined by the bit depth, which is the number of bits per sample in the image data. 3 types of pixel are supported. 3 types of pixel are supported. Yes, that's what they wrote. Bullet point. An index color pixel is represented by a single sample that is an index into a supplied palette. The image bit depth determines the maximum number of palette entries, but not the color precision within the palette. Bullet point. Grayscale pixel is represented by a single sample that is a grayscale level, where 0 is black and the largest value for the bit depth is white. Bullet point. A true color pixel is represented by 3 samples. Red, 0 equals black, max equals red, appears first, then green, 0 equals black, max equals green, then blue, 0 equals black, max equals blue. The bit depth specifies the size of each sample, not the total pixel size. Page 7, RFC-2083. Optionally, grayscale and true color pixels can also include an alpha sample, as described in the next section. Pixels are always packed into scanlines with no wasted bits between pixels. Pixels smaller than a byte never cross byte boundaries. They are packed into bytes with the leftmost pixel in the high order bits of a byte, the rightmost in the low order bits. Permitted bit depths and pixel types are restricted so that in all cases the packing is simple and efficient. It says no wasted bits, but then it's saying that pixels smaller than a byte never cross byte boundaries. That seems a little bit contradictory to me. I think they mean within the cluster of pixels on a scanline, within the contiguous strip of pixels on the scanline, there are no wasted bits, but there's obviously wasted bits on that padding because they just said it in the next sentence. PNG permits multi-sample pixels only with 8 and 16-bit samples, so multiple samples of a single pixel are never packed into one byte. 16-bit samples are stored in network byte order MSB first. Scanlines always begin on byte boundaries. When pixels have fewer than 8 bits and the scanline width is not evenly divisible by the number of pixels per byte, the low-order bits in the last byte of each scanline are wasted. The contents of these wasted bits are unspecified. An additional filter type byte is added to the beginning of every scanline. See filtering, section 2.5. The filter type byte is not considered part of the image data, but it is included in the data stream sent to the compression step. 2.4 Alpha channel. An alpha channel representing transparency information on a per pixel basis can be included in grayscale and true color PNG images. An alpha value of 0 represents full transparency, and a value of 2 to the power of bit depth minus 1 represents a fully opaque pixel. Intermediate values indicate partially transparent pixels that can be combined with a background image to yield a composite image. Thus, alpha is really the degree of opacity of the pixel. but most people refer to alpha as providing transparency information, not opacity information, and we continue that custom here. Alpha channels can be included with images that have either 8 or 16 bits per sample, but not with images that have fewer than 8 bits per sample. Alpha samples are represented with the same bit depth used for the image samples. The alpha sample for each pixel is stored immediately following the grayscale or RGB samples of the pixel. RFC-2083, page 8. The color values stored for a pixel are not affected by the alpha value assigned to the pixel. This rule is sometimes called unassociated or non-premultiplied alpha. Another common technique is to store sample values premultiplied by the alpha fraction. In effect, such an image is already composited against a black background. PNG does not use premultiplied alpha. Transparency control is also possible without the storage cost of a full alpha channel. In an indexed color image, an alpha value can be defined for each palette entry. In grayscale and true color images, a single pixel value can be identified as being transparent. These techniques are controlled by the TRNS ancillary trunk type. Transparency control is also possible without the storage cost of a full alpha channel. In an index color image, an alpha value can be defined for each palette entry. In grayscale and true color images, a single pixel value can be identified as being transparent. These techniques are controlled by the TRNS ancillary chunk type. If no alpha channel nor TRNS chunk is present, all pixels in the image are to be treated as fully opaque. Viewers can support transparency control partially or not at all. See rationale non-premultiplied alpha, section 12.8, recommendations for encoders, alpha channel creation, section 9.4, and recommendation for decoders, alpha channel processing, section 10.8. 2.5. Filtering. PNG allows the image data to be filtered before it is compressed. Filtering can improve the compressibility of the data. The filter step itself does not reduce the size of the data. All PNG filters are strictly lossless. Filtering makes it so the data can be better compressed by the deflate algorithm, because deflate has no conception of a 2D array of image data. It only sees a 1D array of bytes. And so if pixels above and below are very similar, a compression algorithm that has no concept of up and down and only can see left and right within a 1D stream, well, that algorithm isn't going to work very well. So this is like a pre-processing step that makes the deflate algorithm work better. PNG defines several different filter algorithms, including none, which indicates no filtering. The filter algorithm is specified for each scanline by a filter type byte that precedes the filtered scanline in the pre-compressed data stream. An intelligent encoder can switch filters from one scanline to the next. The method for choosing which filter to employ is up to the encoder. See Filter Algorithms, Chapter 6, and Rationale, Filtering, Section 12.9. 2.6. Interlaced Data Order. A PNG image can be stored in interlaced order to allow progressive display. The purpose of this feature is to allow images to fade in when they are being displayed on the fly. Interlacing slightly expands the file size on average, but it gives the user a meaningful display much more rapidly. Note that decoders are required to be able to be read interlaced images whether or not they actually perform progressive display. And I think I butchered that sentence. We're going to go back here. Note that decoders are required to be able to read interlaced images whether or not they actually perform progressive display. So if the image is interlaced, you're still required to be able to read it, even if you don't do that interlacing animation. And we are now on page 9 of RFC-2083. With interlace method 0, pixels are stored sequentially from left to right, and scan lines sequentially from top to bottom, no interlacing. Interlace method 1, known as Adam 7 after its author, Adam M. Costello, consists of 7 distinct passes over the image. Each pass transmits a subset of the pixels in the image. The pass in which each pixel is transmitted is defined by replicating the following 8x8 pattern over the entire image, starting at the upper left corner. And so we have a pattern here. Not sure how to make much sense of this. It would be much better color-coded. So we can see that there are strips here and here. And then I think these numbers are the order in which to render the pixel. So these strips are the last thing to get rendered. There's actually a good animation on Wikipedia for this algorithm in the PNG article on Wikipedia. So if you want to get a better idea what the hell this is, I would recommend looking at their animation. Let's scroll down and keep on reading. Within each pass, the selected pixels are transmitted left to right within the scan line, and selected scan lines sequentially from top to bottom. For example, pass 2 contains pixels 4, 12, 20, etc. of scan lines 0, 8, 16, etc., numbering from 0.0 at the upper left corner. The last pass contains the entirety of scan lines 1, 3, 5, etc. The data within each pass is laid out as though it were a complete image of the appropriate dimensions. For example, if the complete image is 16 by 16 pixels, then pass 3 will contain 2 scan lines, each containing 4 pixels. When pixels have fewer than 8 bits, each such scan line is padded as needed to fill an integral number of bytes. See image layout 2.3. Filtering is done on this reduced image in the usual way, and a filter type byte is transmitted before each of its scan lines. See Filter Algorithms Chapter 6. Notice that the transmission order is defined so that all scan lines transmitted in a pass will have the same number of pixels. This is necessary for proper application of some of the filters. Caution! If the image contains fewer than 5 columns or fewer than 5 rows, some passes will be entirely empty. Encoders and decoders must handle this case correctly. In particular, filter type bytes are only associated with non-empty scan lines. No filter type bytes are present in an empty pass. And that is the end of page 9. Page 10, RFC-2083. See Rationale, Interlacing, Section 12.6, and Recommendations for Decoders, Progressive Display, Section 10.9. 2.7, Gamma Correction. PNG images can specify via the gamma chunk the gamma characteristics of the image with respect to their original scene. Display programs are strongly encouraged to use this information, plus information about the display device they are using, and room lighting to present the image to the viewer in a way that reproduces what the image's original author saw closely as possible. Sorry, I butchered that sentence. It's a run-on sentence, no wonder. All the way back to the top, PNG images can specify via the gamma chunk the gamma characteristics of the image with respect to their original scene. Okay, so that's the first sentence. Display programs are strongly encouraged to use this information, comma, plus information about the display device they are using and room lighting, comma, to present the image to the viewer in a way that closely reproduces the image's original... Display programs are strongly encouraged to use this information plus information about the display device they are using and room lighting to present the image to the viewer in a way that reproduces what the image's original author saw as closely as possible. See Gamma Tutorial Chapter 13 if you aren't already familiar with gamma issues. Gamma correction is not applied to the alpha channel, if any. Alpha samples always represent a linear fraction of full opacity. For high precision applications, the exact chromacity of the RGB data in a PNG image can be specified via the CHRM chunk, allowing more accurate color matching than gamma correction alone will provide. See Color Tutorial Chapter 14 if you aren't already familiar with color representation issues. See Rationale, Why Gamma, Section 12.7, Recommendations for Encoders, encoding gamma handling, section 9.2, and recommendations for decoders, decoder gamma handling, section 10.5. 2.8 Text strings. A PNG file can store text associated with the image, such as an image description or copyright notice. Keywords are used to indicate what each text string represents. ISO 8859-1 Latin 1 is the character set recommended for use in text strings. ISO-8859. This character set is a superset of 7-bit ASCII. So I'm going to guess that's 8-bit ASCII with those extended ASCII sequences and those weird boxes and things and whatnot. Character codes not defined in Latin 1 should not be used because they have no platform-independent meaning. If a non-Latin 1 code does appear in a PNG text string, its interpretation will vary across platforms and decoders. Some systems might not even be able to display all the characters in Latin 1, but most modern systems can. Provision is also made for the storage of compressed text. See Rationale Text Strings, section 12.10. RFC-2083, page 11. 3. File structure. A PNG file consists of a PNG signature followed by a series of chunks. This chapter defines the signature and the basic properties of chunks. Individual chunk types are discussed in the next chapter. 3.1 PNG file signature. The first 8 bytes of a PNG file always contain the following decimal values: 137, 80, 78, 71, 13, 10, 26, and 10. This signature indicates that the remainder of the file contains a single PNG image consisting of a series of chunks beginning with an IHDR chunk and ending with an IEND chunk. See Rationale, PNG file signature, section 12.11. 3.2 Chunk layout. Each chunk consists of 4 parts. Length, a 4-byte unsigned integer giving the number of bytes in the chunk's data field. The length counts only the data field, not itself. The chunk type code, or the CRC, 0 is a valid length. Although encoders and decoders should treat the length as unsigned, its value must not exceed 2 to the power of 31 minus 1 bytes. Chunk type, a 4-byte chunk type code. For convenience in description and examining PNG files, type codes are restricted to consist of uppercase and lowercase ASCII letters, uppercase AZ and AZ lowercase, or 65 through 90 and 97 through 122 decimals. It doesn't sound like there's any ASCII numbers, and honestly, ASCII numbers could get kind of confusing. However, encoders and decoders must treat the codes as fixed binary values, not character strings. For example, it would not be correct to represent the type code IDAT, IDAT, by the EBCDIC equivalents of those characters. Additionally, naming conventions for chunk types are discussed in the next section. Really quick, so EBCDIC character set, what I'm noticing here is if we look at some of the letters, if we go down to where the letters are, they're kind of like broken apart. So look at, right, we got J through R, and then there's this space sequentially with these decimal and hex values, and then there's some more letters, right? So they're not contiguous chunks for these letters, whereas ASCII, if we look at the letters section is contiguous, right? 65 to 90 uppercase, and then lowercase 97 to 122, right? It's a contiguous strip. So definitely the binary representation of ASCII and this, what is this again? This is EBCDIC. They're different. You're going to have a different bit pattern for an A in this EBCDIC than you are in ASCII. So that's why the spec is saying that about it's not valid to represent it as like whatever this is. Okay, so I just wanted to make sure I understood that. And let's keep on going. So chunk data. Chunk data. The data bytes appropriate to the chunk type, if any. This field can be of 0 length. Okay, we're on page 12 of RFC-2083. CRC, a 4-byte CRC cyclic redundancy check calculated on the preceding bytes in the chunk, including the chunk type code and chunk data fields, but not including the length of the field. The CRC is always present even for chunks containing no data. The CRC algorithm 3.4. So section 3.4 for more information on that. The chunk data length can be any number of bytes up to the maximum, therefore implementers cannot assume that the chunks are aligned on any boundaries larger than bytes. Chunks can appear in any order subject to the restrictions placed on each chunk type. One notable restriction is that IHDR must appear first and IEND must appear last. Thus, the IEND chunk serves as an end of file marker. Multiple chunks of the same type can appear, but only if specifically permitted for that type. See rationale, chunk layout, section 12.12. 3.3, chunk naming conventions. Chunk type codes are assigned so that the decoder can determine some properties of a chunk even when it does not recognize the type code. These rules are intended to allow safe, flexible extension of the PNG format by allowing a decoder to decide what to do when it encounters an unknown chunk. The naming rules are not normally of interest when the decoder does recognize the chunk's type. Right? It only matters when you don't recognize it. Then you can look at the naming rules and figure out if it is ancillary or critical. 4 bits of the type code, namely bit 5, value 32, of each byte are used to convey chunk properties. This choice means that a human can read off the assigned properties according to whether each letter of the type code is uppercase, bit 5 is 0, or lowercase, bit 5 is 1. However, decoders should test the properties of an unknown chunk by numerically testing the specified bits, testing whether a character is uppercase or lowercase is inefficient, and even incorrect if a locale-specific case definition is used. It is worth noting that the property bits are an inherent part of the chunk name, and hence are fixed for any chunk type. Thus, text and text would be unrelated chunk type codes, not the same chunk with different properties. Decoders must recognize type codes by a simple 4-byte literal comparison. It is incorrect to perform case conversion on type codes. So they are case sensitive. Alright, so page 13 of RFC 2083. The semantics of the property bits are: ancillary bit. Bit 5 of the first byte, 0 uppercase equals critical, 1 lowercase equals ancillary. Chunks that are not strictly necessary in order to meaningfully display the contents of the file are known as ancillary chunks. A decoder encountering an unknown chunk in which the ancillary bit is 1 can safely ignore the chunk and proceed to display the image. The time chunk, TIME, is an example of an ancillary chunk. Chunks that are necessary for a successful display of the file's contents are called critical chunks. A decoder encountering an unknown chunk in which the ancillary bit is 0 must indicate to the user the image contains information it cannot safely interpret. The image header chunk IHDR is an example of a critical chunk. Private bit, bit 5 of second byte, 0 uppercase equals public, 1 lowercase equals private. A public chunk is one that is part of the PNG specification or is registered in the list of PNG special-purpose public chunk types. Applications can also define private, unregistered chunks for their own purposes. The names of private chunks must have a lowercase second letter, while public chunks will always be assigned names with uppercase second letters. Note that decoders do not need to test the private chunk property bit since it has no functional significance. It is simply an administrative convenience to ensure that public and private chunk names will not conflict. See additional chunk types, section 4.4, and recommendations for encoders. Use of private chunks, section 9.8. Reserved bit, bit 5 of third byte, must be 0 uppercase in files conforming to this version of PNG. The significance of the case of the third letter of the chunk name is reserved for possible future expansion. At the present time, all chunk names must have uppercase third letters. Decoders should not complain about a lowercase third letter, however, as some future version of PNG specification could define a meaning for this bit. It is sufficient to treat a chunk with a lowercase third letter in the same way as any other unknown chunk type. Safe to copy bit, bit 5 of fourth byte. 0 equals uppercase, unsafe to copy, 1 equals lowercase, safe to copy. This property bit is not of interest to pure decoders, but it is needed by PNG editors, programs that modify PNG files. This bit defines the proper handling of unrecognized chunks in a file that is being modified. If a chunk's safe to copy bit is 1, the chunk may be copied to a modified PNG file whether or not the software recognizes the chunk type, and regardless of the extent of the file modifications. If the chunk's safe to copy bit is 0, it indicates that the chunk depends on the image data. If the program has made any changes to critical chunks, including addition, modification, deletion, or reordering of critical chunks, then unrecognized unsafe chunks must not be copied to the output PNG file. Of course, if the program does recognize the chunk, it can choose to output an appropriately modified version. A PNG editor is always allowed to copy all unrecognized chunks if it has only added, deleted, modified, or reordered ancillary chunks. This implies that it is not permissible for ancillary chunks to depend on other ancillary chunks. PNG editors that do not recognize a critical chunk must report an error and refuse to process that PNG file at all. The safe/unsafe mechanism is intended for use with ancillary chunks. The safe to copy bit will always be 0 for critical chunks. Rules for PNG editors are discussed further in Chunk Ordering Rules, Chapter 7. For example, the hypothetical chunk type name blob has the property bits blob, B-L-O-B, 32-bit chunk type code represented in text form, and the least significant bit is safe to copy bit is 1, lowercase letter, bit 5 is 1. The O is a reserved bit is 0. Uppercase letter, bit 5 is 0. We have a capital L, private bit is 0. Uppercase letter, bit 5 is 0. And then we have the lowercase b at the very beginning. Ancillary bit is 1. Lowercase letter, bit 5 is 1. So it's saying that in order to determine if it is uppercase or a lowercase letter, we can just look at bit number 5 of the ASCII, and that will tell us whether or not the letter is uppercase or lowercase, which is a nice little hack I did not know about. And as long as we assume that they are always ASCII letters, that is a check you can safely do. Okay, therefore, this name represents an ancillary public safe-to-copy chunk. Alright, so now, what page are we on here? This is page 15 of RFC 2083, C Rationale, Chunk Naming Conventions, Section 12.3, 3.4, CRC Algorithm. Chunk CRCs are calculated using standard CRC methods with pre- and post-conditioning as defined by ISO 3309, ISO-3309, or ITU-T V.42, ITU-V42, I believe those are links. The CRC polynomial employed is, oh boy, x to the power of 32 plus x to the power of 26 plus x to the power of 23 plus x to the power of 22 plus x to the power of 16 plus x to the power of 12 plus x to the power of 11 plus x to the power of 10 plus x to the power of 8 plus x to the power of 7 plus x to the power of 5 plus x to the power of 4 plus x to the power of 2 plus x plus 1. Oh boy, yeah. The 32-bit CRC registered in this 32-bit CRC register is initialized to all ones, and then the data from each byte is processed from the least significant bit 1 to the most significant bit, 128, so it's the values of those bits, not the positions. After all the data bytes are processed, the CRC register is inverted, its ones complement is taken. This value is transmitted, stored in the file MSB first. For the purpose of separating into bytes and ordering, the least significant bit of the 32-bit CRC is defined to be the coefficient of the x to the power of 31st term. And I don't know my math very well, so I'm not sure what that means. Practical calculation of the CRC always employs a pre-calculated table to greatly accelerate the computation. See Sample CRC Code, Chapter 15. 4. Chunk specifications. This chapter defines the standard types of PNG chunks. 4.1 Critical chunks. All implementations must understand and successfully render the standard critical chunks. A valid PNG must contain an IHDR chunk, one or more IDAT chunks, and an IEND chunk. 4.1.1 IHDR image header. The IHDR chunk must appear first. It contains width 4 bytes, height 4 bytes, bit depth 1 byte, color type 1 byte, compression method 1 byte, filter method 1 byte, and interlace method 1 byte. RFC-2083, page 16, PNG Portable Network Graphics, March 1997. Width and height give the image dimensions in pixels. They are 4-byte integers. 0 is an invalid value. The maximum for each is 2 to the power of 31 minus 1 in order to accommodate languages that have difficulty with unsigned 4-byte values. Bit depth is a single byte integer, giving the number of bits per sample or per palette index, not per pixel. Valid values are 1, 2, 4, 8, and 16, although not all values are allowed for all color types. Color type is a single byte integer that describes the interpretation of the image data. Color type codes represent sums of the following values: 1. Palette used, 2. Color used, and 4. Alpha channel used. Valid values are 0, 2, 3, 4, and 6. Bit depth restrictions for each color type are imposed to simplify implementations and to prohibit combinations that do not compress well. Decoders must support all legal combinations of bit depth and color type. The allowed combinations are: we have columns color type, allowed bit depth, and interpretation. First record. Color type 0, allowed bit depths 1, 2, 4, 8, 16. Interpretation: each pixel is a grayscale sample. Color type 2, this is the second record. Color type 2, allowed bit depths 8 and 16. The interpretation is each pixel is an RGB triple. The third record, the color type is 3. Allowed bit depths is 1, 2, 4, and 8. Interpretation: each pixel is a palette index. A PLTE chunk must appear. The fourth record, allowed bit depths are 8 and 16. Oh, and the color type is 4. So it's been quite coincidental, but the record number and the color type have been mostly matching, except for the first. Color type 4, allowed bit depths 8 and 16. Interpretation: each pixel is a grayscale sample, followed by an alpha sample. The final record, record 5, the color type is 6, and the allowed bit depths are 8 and 16. The interpretation: each pixel is an RGB triple, followed by an alpha sample. The sample depth is the same as the bit depth, except in the case of color type 3, in which the sample depth is always 8 bits. Compression method is a single byte integer that indicates the method used to compress the image data. At present, only compression method 0, deflate/inflate compression with a 32K sliding window is defined. All standard PNG images must be compressed with this scheme. The compression method field is provided for possible future expansion or proprietary variants. Decoders must check this byte and report an error if it holds an unrecognized code. See deflate/inflate compression, Chapter 5 for details. Filter method is a single byte integer that indicates the pre-processing method applied to the image data before compression. At present, only filter method 0, adaptive filtering with 5 basic filter types, is defined. As with the compression method field, decoders must check this byte and report an error if it holds an unrecognized code. See Filter Algorithms, Chapter 6 for details. Interlace method is a single byte integer that indicates the transmission order of the image data. Two values are currently defined: 0, no interlace, or 1, Atom 7 interlace. See Interlace Data Order, section 2.6 for details. 4.1.2 PLTE palette. The PLTE chunk contains from 1 to 256 palette entries, each a 3-byte series of the form red, 1 byte, 0 equals black, 255 equals red; green, 1 byte, 0 equals black, 255 equals green; blue, 1 byte, 0 equals black, 255 equals blue. The number of entries is determined from the chunk length. A chunk length not divisible by 3 is an error. This chunk must appear for color type 3. It can appear for color types 2 and 6. It must not appear for color types 0 and 4. If this chunk does appear, it must precede the first IDAT chunk. There must not be more than one PLTE chunk. For color type 3 index color, the PLTE chunk is required. The first entry in PLTE is referenced by pixel value 0. The second pixel value 1, etc. The number of palette entries must not exceed the range that can be represented in the image bit depth. For example, 2 to the power 4 equals 16 for a bit depth of 4. It is permissible to have fewer entries than the bit depth would allow. In this case, any out-of-range pixel value found in the image data is an error. For color types 2 and 6, true color and true color with alpha, the PLTE chunk is optional. If present, it provides a suggested set of from 1 to 256 colors to which the true color image can be quantized if the viewer cannot display true color directly. If PLTE is not present, such a viewer will need to select colors on its own, but it is often preferable for this to be done once by the decoder. See Recommendations for Encoders, Suggested Palettes, section 9.5. Note that the palette uses 8 bits, 1 byte per sample, regardless of the image bit depth specification. In particular, the palette is 8 bits deep, even when it is a suggested quantization of a 16-bit true color image. There is no requirement that the palette entries all be used by the image, nor that they all be different. 4.1.3 IDAT image data. The IDAT chunk contains the actual image data. To create this data, begin with image scan lines represented as described in Image Layout, section 2.3. The layout and total size of this raw data are determined by the fields of IHDR. Filter the image data according to the filtering method specified by the IHDR chunk. Note that with filter method 0, the only one currently defined, this implies prepending a filter type byte to each scan line. Compress the filter data using the compression method specified by the IHDR chunk. The IDAT chunk contains the output data stream of the compression algorithm. To read the image data, reverse this process. There can be multiple IDAT chunks. If so, they must appear consecutively with no other intervening chunks. The compressed data stream is the concatenation of the contents of all the IDAT chunks. The encoder can divide the compressed data stream into IDAT chunks however it wishes. Multiple IDAT chunks are allowed so that encoders can work in a fixed amount of memory. Typically, the chunk size will correspond to the encoder's buffer size. It is important to emphasize that IDAT chunk boundaries have no semantic significance and can occur at any point in the compressed data stream. A PNG file in which each IDAT chunk contains only 1 data byte is legal, although remarkably wasteful of space. For that matter, 0-length IDAT chunks are legal, although even more wasteful. See Filter Algorithms, Chapter 6, and Deflate/Inflate Compression, Chapter 5 for details. End of page 18, RFC-2083. 4.1.4 I-End Image Trailer. The IN chunk must appear last. It marks the end of the PNG data stream. The chunk's data field is empty. 4.2 Ancillary chunks. All ancillary chunks are optional, in the sense that encoders need not write them and decoders can ignore them. However, encoders are encouraged to write the standard ancillary chunks when the information is available, and decoders are encouraged to interpret these chunks when appropriate and feasible. The standard ancillary chunks are listed in alphabetical order. This is not necessarily the order in which they would appear in a file. 4.2.1 BKGD background color. The BKGD chunk specifies a default background color to present the image against. Note that viewers are not bound to honor this chunk. A viewer can choose to use a different background. For color type 3 index color, the BKGD chunk contains palette index 1 byte. The value is the palette index of the color to be used as background. For color types 0 and 4, grayscale without alpha, BKG contains gray, 2 bytes, range 0, ... within parentheses to the power of bit depth, and then -1. For consistency, 2 bytes are used regardless of the image bit depth. The value is the gray level to be used as background. For color types 2 and 6, true color or with or without alpha, BKGD contains red, green, and blue, and they are all 2 bytes, and they all have the range 0 to 2 to the power of bit depth -1. So saying that in the way it's written, red, 2 bytes, range 0, ... open paren, 2, bit depth, close paren, -1, green, 2 bytes, comma, range 0, ... open paren, 2, power, bit depth, close paren, -1, blue, 2 bytes, comma, range 0, ... open paren, 2, bit depth, close paren, -1. For consistency, 2 bytes per sample are used regardless of the image bit depth. This is the RGB color to be used as background. When present, the BKGD chunk must precede the first IDAT chunk and must follow the PLTE chunk, if any. See Recommendations for Decoders, Background Color, Section 10.7. 4.2.2 CHRM Primary, Chromatices, and White Point. Applications that need device-independent specifications of colors in a PNG file can use the CHRM chunk to specify the 1931 CIE X, Y chromatices of the red, green, and blue primaries used in the image, and the reference white point. See Color Tutorial Chapter 14 for more information. The CHRM chunk contains white point X 4 bytes, white point Y 4 bytes, red X 4 bytes, red Y 4 bytes, green X 4 bytes, green Y 4 bytes, blue X 4 bytes, blue Y 4 bytes. Each value is encoded as a 4-byte unsigned integer representing the X or Y value multiplied by 100,000, I believe. Yes, that looks like 100,000. There are 1, 2, 3, 4, 5 zeros. For example, in a value of 0.3127 would be stored as integer 31270. CHRM is allowed in all PNG files, although it is of little value for grayscale images. If the encoder does not know the chromaticity values, it should not write a CHRM chunk. The absence of a CHRM chunk indicates that the image's primary colors are device dependent. If the CHRM chunk appears, it must precede the first IDAT chunk, and it must also precede the PLTE chunk if present. See Recommendations for Encoders, Encoder Color Handling, Section 9.3, and Recommendations for Decoders, Decoder Color Handling, Section 10.6. End of page 20, RFC-2083. Next section, 4.2.3, Gamma Image Gamma. 4.2.3, Gamma Image Gamma. The gamma chunk specifies the gamma of the camera or simulated camera that produced the image, and thus the gamma of the image with respect to the original scene. More precisely, the gamma chunk encodes the file gamma value as defined in Gamma Tutorial Chapter 13. The gamma chunk contains image gamma, 4 bytes. The value is encoded as a 4-byte unsigned integer representing gamma multiplied by 100,000. For example, a gamma of 0.45 would be stored as the integer 45000, in other words, 45,000. If the encoder does not know the image's gamma value, it should not write a gamma chunk. The absence of a gamma chunk indicates that the gamma is unknown. If the gamma chunk appears, it must precede the first IDAT chunk, and it must also precede the PLTE chunk if present. See Gamma Correction, Section 2.7, Recommendations for Encoders, Encoder Gamma Handling, Section 9.2, and Recommendations for Decoders, Decoder Gamma Handling, Section 10.5. 4.2.4 HIST image histogram, and that's lowercase h and then the uppercase I, uppercase S, uppercase T. The HIST chunk gives the approximate usage frequency of each color in the color palette. A histogram chunk can appear only when a palette chunk appears. If a viewer is unable to provide all the colors listed in the palette, the histogram may help it decide how to choose a subset of the colors for display. The HIST chunk contains a series of 2-byte, 16-bit unsigned integers. There must be exactly one entry for each entry in the PLTE chunk. Each entry is proportional to the fraction of pixels in the image that have that palette index. The exact scale factor is chosen by the encoder. Histogram entries are approximate, with the exception that a 0 entry specifies that the corresponding palette entry is not used at all in the image. It is required that the histogram entry be non-zero if there are any pixels of that color. End of page 21, RFC-2083. When the palette is a suggested quantization of a true color image, the histogram is necessarily approximate, since a decoder may map pixels to palette entries differently than the encoder did. In this situation, 0 entries should not appear. The HIST chunk, if it appears, must follow the PLTE chunk and must precede the first IDAT chunk. See Rationale, Palette Histograms, Section 12.4, and Recommendations for Decoders, Suggested Palette and Histogram Usage, Section 10.10. 4.2.5 PHYS Physical Pixel Dimensions. The PHYS chunk specifies the intended pixel size or aspect ratio for display of the image. It contains record 1 pixels per unit, x-axis, 4 bytes unsigned integer, record 2 pixels per unit, y-axis, 4 bytes unsigned integer, and the final record, record 3, unit specifier 1 byte. The following values are legal for the unit specifier. 0, unit is unknown. 1, unit is the meter. When the unit specifier is 0, the PHYS chunk defines pixels, aspect ratio only. The actual size of the pixels remain unspecified. I'm going to say that again because I think I screwed that up. When the unit specifier is 0, the PHYS chunk defines pixel aspect ratio only, semicolon. The actual size of the pixels remains unspecified. Conversion note. 1 inch is equal to exactly 0.0254 meters. If this ancillary chunk is not present, pixels are assumed to be square, and the physical size of each pixel is unknown. If present, this chunk must precede the first IDAT chunk. 4.2.6 S-bit significant bits. To simplify decoders, PNG specifies that only certain sample depths can be used, and further specifies that sample values should be scaled to the full range of possible values at the sample depth. However, the S-bit chunk is provided in order to store the original number of significant bits. This allows decoders to recover the original data losslessly even if the data had a sample depth not directly supported by PNG. We recommend that an encoder omit and S-bit chunk if it has converted the data from a lower sample depth. And we are on the beginning of page 23. This paragraph spanned pages 22 and 23. We're on RFC-2083, PNG Portable Network Graphics. For color type 0 grayscale, the S-bit chunk contains a single byte indicating the number of bits that were significant in the source data. For color type 2 true color, the S-bit chunk contains 3 bytes indicating the number of bits that were significant in the source data for the red, green, and blue channels, respectively. For color type 3 index color, the S-bit contains 3 bytes indicating the number of bits that were significant in the source data for the red, green, and blue components of the palette entries, respectively. For color type 4 grayscale with alpha channel, the S-bit chunk contains 2 bytes indicating the number of bits that were significant in the source grayscale data and the source alpha data, respectively. For color type 6 true color with alpha channel, the S-bit chunk contains 4 bytes indicating the number of bits that were significant in the source data for red, green, blue, and alpha channels, respectively. Each depth specified in S-bit must be greater than 0 and less than or equal to the sample depth, which is 8 for index-colored images, and the bit depth given in IHDR for other color types. A decoder need not pay attention to S-bit : the stored image is a valid PNG file of the sample depth indicated by IHDR. However, if a decoder wishes to recover the original data at its original precision, this can be done by right-shifting the stored samples, open paren, the stored palette entries, for an indexed color image, close paren period. The encoder must scale the data in such a way that the high order bits match the original data, period. If the S-bit chunk appears, it must precede the first IDAT chunk, and it must also precede the PLTE chunk if present. See Recommendations for Encoders, Sample Depth Scaling, Section 9.1, and Recommendations for Decoders, Sample Depth Rescaling, Section 10.4. End of page 23, RFC 2083. 4.2.7, Text, textual data. That's lowercase t, capital E, capital X, lowercase t. Textual information that the encoder wishes to record with the image can be stored in TEXT chunks. Each TEXT chunk contains a keyword and a text string in the format record 1, keyword, 1 to 79 bytes, character string. Record 2, null separator, 1 byte. Final and third record, text, n bytes, character string. The keyword and text string are separated by a 0-byte null character. Neither the keyword nor the text string can contain a null character. Note that the text string is not null terminated. The length of the chunk is sufficient information to locate the ending. Keyword must be at least 1 character and less than 80 characters long. The text string can be of any length from 0 bytes up to the maximum permissible chunk size, less than the length of the keyword and separator. Any number of TEXT chunks can appear, and more than one with the same keyword is permissible. The keyword indicates the type of information represented by the text string. The following keywords are predefined and should be used where appropriate. Title, short, one-line title or caption for image, author, name of image's creator, description of image, possibly long, copyright notice, creation time of original image creation, software used to create the image, disclaimer, legal disclaimer, warning of nature of content, source, device used to create the image, comment, miscellaneous comment, conversion from GIF comment. For the creation time period, the date format defined in section 5.2.14 of RFC-2083 is suggested but not required. RFC-1123, it looks like that's a link. Decoders should allow for free format text associated with this or any other keyword. Other keywords may be invented for other purposes. Keywords of general interest can be registered with the maintainers of the PNG specification. However, it is also permitted to use private unregistered keywords. Private keywords should be end of page 24. Private keywords should be reasonably self-explanatory in order to minimize the chance that the same keyword will be used for incompatible purposes by different people. Both keyword and text are interpreted according to the ISO 8859-1 Latin 1 character set, ISO 8859. The text string can contain any Latin 1 character. New lines in the text string should be represented by a single line feed character, decimal 10. Use of other control characters in the text is discouraged. Keywords must contain only printable Latin 1 characters and spaces, that is, only character codes 32 through 126 and 161 through 255 decimal are allowed. To reduce the chances for human misreading of a keyword, leading and trailing spaces are forbidden, and consecutive space, as are consecutive spaces. Note also that the non-breaking space code, code 160, is not permitted in keywords since it is visually indistinguishable from an ordinary space. Keywords must be spelled exactly as registered so that decoders can use simple literal comparisons when looking for particular keywords, and particular keywords are considered case sensitive. See Recommendations for Encoders, Text Chunk Processing, Section 9.7, and Recommendations for Decoders, Text Chunk Processing, Section 10.11. 4.2.8 Time Image Last Modification Time. The time chunk gives the time of the last image modification, not the time of initial image creation. It contains year, 2 bytes, complete for example 1995, not 95. Month, 1 byte, 1 to 12. Day, 1 byte, 1 to 31. Hour, 1 byte, 0 to 23. Minute, 1 byte, 0 to 59. Second, 1 byte, 0 to 60. Yes, 60 for leap seconds, not 61, a common error. Okay, that makes sense because 0 to 60 would be 61 unique values. That would not be 61. Okay, makes sense. Universal time UTC, also called GMT, should be specified rather than local time. End of page 25. We're on RFC-2083. The time chunk is intended for use as an automatically applied timestamp that is updated whenever the image data is changed. It is recommended that the time not be changed by PNG editors that do not change the image data. See also the creation time text keyword, which can be used for a user-supplied time. 4.2.9 TRNS transparency. The TRNS chunk specifies that the image uses simple transparency, either alpha values associated with palette entries for index color images, or a single transparent color for grayscale and true color images. Although simple transparency is not as elegant as the full alpha channel, it requires less storage space and is sufficient for many common cases. For color type 3 index color, the TRNS chunk contains a series of 1 byte alpha values corresponding to entries in the PLTE chunk. Alpha for palette index 0, 1 byte, alpha for palette index 1, 1 byte, etc. Each entry indicates that pixels of the corresponding palette index must be treated as having the specified alpha value. Alpha values have the same interpretation as in an 8-bit full alpha channel. 0 is fully transparent, 255 fully opaque, regardless of the image bit depth. The TRNS chunk must not contain more alpha values than there are palette entries, but TRNS can contain fewer values than there are palette entries. In this case, the alpha value for all remaining palette entries is assumed to be 255. In the common case, in which only palette index 0 need be made transparent, only a 1 byte TRNS chunk is needed. For color type 0 grayscale, the TRNS chunk contains a single gray level value stored in the format gray 2 bytes range 0 ... 2 to the power of bit depth minus 1. For consistency, 2 bytes are used regardless of the image bit depth. Pixels of the specified gray level are also treated as transparent, equivalent to alpha value 0. All other pixels are to be treated as fully opaque, alpha value 2 to the power of bit depth minus 1. End of page 26. We're in RFC-2083, Portable Network Graphics, March 1997. For color type 2, true color, the TRNS chunk contains a single RGB color value stored in the format red 2 bytes range 0 to bit depth to the power, red 2 bytes range 0 to 2 to the power of bit depth minus 1, green 2 bytes range 0 to 2 to the power of bit depth minus 1, and blue 2 bytes range 0 to 2 to the power of bit depth minus 1. So that's red, green, and blue, and they're all within the range of 0 to the power of bit depth minus 1, and you require 2 bytes to get that much information. Alright. For consistency, 2 bytes per sample are used regardless of the image bit depth. Pixels of the specified color value are to be treated as transparent, equivalent to alpha value 0. All other pixels are to be treated as fully opaque, alpha value 2 to the power of bit depth minus 1. TRNS is prohibited for color types 4 and 6, since full alpha channel is already present in those cases. Note, when dealing with 16-bit grayscale or true color data, it is important to compare both types of sample values to determine whether a pixel is transparent. Although decoders may drop the low-order byte of those samples for display, this must not occur until after the data has been tested for transparency. For example, if the grayscale level 0x0001 is specified to be transparent, it would be incorrect to compare only the high-order byte and decide that 0x0002 is also transparent. When present, the TRNS chunk must precede the first IDAT chunk and must follow the PLTE chunk, if any. 4.2.10 ZTXT, so that's lowercase z, capital T, capital X, lowercase t. Compressed textual data. The ZTXT chunk contains textual data, just as TEXT does. However, ZTXT takes advantage of compression. ZTXT and TXT chunks are semantically equivalent, but ZTXT is recommended for storing large blocks of text. A ZTXT chunk contains keyword 1 to 79 bytes, character string, null separator 1 byte, compression method 1 byte, compressed text n number of bytes. The keyword and null separator are exactly the same as the TEXT chunk. Note that the keyword is not compressed. The compression method byte identifies the compression method used in the ZTXT chunk. The only value presently defined for it is 0, deflate/inflate compression. The compression method byte is end of page 27. On to page 28 of RFC-2083, the compression method byte is followed by a compressed data stream that makes up the remainder of the chunk. For compression method 0, the data stream adheres to the zlib data stream format. See deflate/inflate compression, chapter 5. Decompression of this data stream yields Latin 1 text and is identical to the text that would be stored in the equivalent TEXT chunk. Any number of ZTXT and TEXT chunks can appear in the same file. See the preceding definition of the TEXT chunk for the predefined keywords and the recommended format of the text. See recommendations for encoders, text chunk processing, section 9.7, and recommendations for decoders, text chunk processing, section 10.11. 4.3 Summary of standard chunks. This table summarizes some of the properties of the standard chunk types. Critical chunks must appear in this order, except PLTE is optional. Name, multiple, OK, question mark, ordering constraints. So we have 3 columns here: name, multiple OK, question mark, and ordering constraint. And we have 4 records here. We have a IHDR, PLTE, IDAT, and IN. Those are 4 records going by the name of the name within the name column. So the first record, IHDR, multiple OK is no. So you can only have one IHDR chunk. And the ordering constraint is it must be first. The PLTE chunk, our second record, multiple OK is no. And the order constraint is it must be before IDAT. The third record, IDAT, multiple OK, yes. Ordering constraint, multiple IDATs must be consecutive. The final record, number 4, IEND, multiple OK, no, and the order constraint is must be last. Ancillary chunks need not appear in this order. We have name, multiple OK, and ordering constraint columns. And we have many more records, more than I can count by just looking at. So I'm going to count through them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 records here. So the different records going by name are CHRM with a lowercase c and then everything else is capital. Gamma with a lowercase g. Name. SBIT, lowercase s. BKGD, lowercase b. HIST with a lowercase h. TRNS with a lowercase t. So all of those chunks just start with a lowercase and the rest are capital. PHYS has lowercases on both ends. Time also has, time only has a lowercase t on the front. TEXT has lowercase t's on both sides, and ZTXT is a lowercase z, and then on the end has a lowercase t. Okay, so reading through this chart, record number 1, CHRM, lowercase c, capital H, capital R, capital M, CHRM, multiple OK, no, ordering constraint before PLTE and IDAT, gamma, lowercase g, and then AMA is uppercase, multiple OK, no, before PLTE and IDAT. The third record, SBIT, lowercase s, capital B, capital I, capital T, multiple OK, no, before PLTE and IDAT. BKGD, lowercase b, capital K, capital G, capital D, multiple OK, no, after PLTE, before IDAT. HIST, lowercase h, capital I, capital S, capital T, multiple OK, no, after PLTE, before IDAT. TRNS, lowercase t, capital R, capital N, capital S, multiple OK, no, after PLTE, before IDAT. PHYS, lowercase p, the capital H, capital Y, and lowercase s, multiple OK is no, and the ordering constraint is before IDAT. Time with a lowercase t, capital I, capital M, capital E, multiple OK, no. Ordering constraint, none. TEXT, lowercase t, uppercase E, uppercase X, lowercase t, multiple OK, yes. Ordering constraint, none. ZTXT, multiple OK, yes. Ordering constraint is none. And ZTXT is lowercase z, capital T, capital X, lowercase t. End of page 28 of RFC 2083, PNG Portable Network Graphics, March 1997. Standard keywords for text and ZTXT chunks. Title, short, one-line title or caption for image. Author, name of image's creator. Description, description of image, possibly long. Copyright, copyright notice. Creation time, time of original image creation. Software, software used to create the image. Disclaimer, legal disclaimer. Warning, warning of the nature of the content. Source, device used to create the image. Comment, miscellaneous comment. Conversion from GIF comment. Right, so we have 4.4 additional chunk types. 4.4 additional chunk types. Additional public PNG chunk types are defined in the comment. In the document, PNG special purpose public chunks. PNG extensions chunks described here. There are expected to be less widely supported than those defined in the specification. However, application authors are encouraged to use those chunk types whenever appropriate for their applications. Additional chunk types can be proposed for inclusion in that list by contacting the PNG specification maintainers at png-info@uu.net or at png-group@w3.org. All right. New public chunks will only be registered if they are of use to others and do not violate the design philosophy of PNG. Chunk registration is not automatic, although it is the intent of the authors that it be straightforward when a new chunk of potentially wide application is needed. Note that the creation of new critical chunk types is discouraged unless absolutely necessary. Applications can also use private chunk types to carry data that is not of interest to other applications. See recommendations for encoders' use of private chunks, section 9.8. Decoders must be prepared to encounter unrecognized public or private chunk type codes. Unrecognized chunk types must be handled as described in Chunk Naming Conventions, Section 3.3. 5. Deflate/inflate compression. PNG compression method 0, the only compression method presently defined for PNG, specifies deflate/inflate compression with a 32K sliding window. Deflate compression is an LZ77 derivative used in zip, gzip, pkzip, and related programs. Extensive research has been done supporting its patent-free status. Portable C implementations are widely available. End of page 29 of the RFC-2083 Portable Network Graphics. On to page 30. Deflate compressed data streams with PNG are stored in the zlib format, which has the structure compression method /flags code 1 byte, additional flags /check bits 1 byte, compressed data blocks n bytes, and the check value is 4 bytes. Further details on this format are given in the zlib specification RFC-2083, so I need to read that. For PNG compression method 0, the zlib compression method /flag code must specify method code 8 deflate compression and an LZ77 window size of not more than 32K. Note that the zlib compression method number is not the same as the PNG compression method number. The additional flags must not specify a present dictionary. I'm not sure what they mean by present dictionary, but we'll keep on going. The compressed data within the zlib data stream is stored as a series of blocks, each of which can represent raw, uncompressed data, LZ77 compressed data encoded with fixed Huffman codes, or LZ77 compressed data encoded with custom Huffman codes. A marker bit in the final block identifies it as the last block, allowing the decoder to recognize the end of the compressed data stream. Further details on the compression algorithm and the encoding are given in the deflate specification, RFC-1951, so I still need to read that. The check value stored at the end of the zlib data stream is calculated on the uncompressed data and represented by the data stream. Note that the algorithm used is not the same as the CRC calculation used for PNG chunk check values. The zlib check value is useful mainly as a cross-check that the deflate and inflate algorithms are implemented correctly. Verifying the chunk CRCs provides adequate confidence that the PNG file has been transmitted undamaged. In a PNG file, the concatenation of the contents of all IDAT chunks makes up a zlib data stream as specified above. This data stream decompresses to filtered image data as described elsewhere in this document. It is important to emphasize that the boundaries between IDAT chunks are arbitrary and can fall anywhere in the zlib data stream. There is not necessarily any correlation between IDAT chunk boundaries for deflate block boundaries or any other feature of the zlib data. For example, it is entirely possible for the terminating zlib check value to be split across IDAT chunks. End of page 30 of RFC 2083. We're on page 31 now. In the same vein, there is no required correlation between the structure of the image data, i.e. scanline boundaries, and deflate block boundaries or IDAT chunk boundaries. The complete image data is represented by a single zlib data stream and is stored in some number of IDAT chunks. The decoder that assumes any more than this is incorrect. Of course, subencoder implementations may emit files in which some of these structures are indeed related, but decoders cannot rely on this. PNG also uses zlib data streams in ztxt chunks. In a ztxt chunk, the remainder of the chunk following the compression method byte is a zlib data stream as specified above. This data stream decompresses to the user-readable text described by the chunk's keyword. Unlike the image data, such data streams are not split across chunks. Each ztxt chunk contains an independent zlib data stream. Additional documentation and portable C code for deflate and inflate are available from the info-zip archives at open, what do you call this? Open, let's just call it a less than symbol, because I don't know what the other word for it is. Less than URL //ftp://ftp.uu.net/pub/archiving/ greater than, and then a period. Filter algorithms. This chapter describes the filter algorithms that can be applied before compression. The purpose of these filters is to prepare the image data for optimum compression. 6.1 filter types. PNG filter method 0 defines 5 basic filter types. Okay, so we have 2 columns here. We have type and name. The types are 0, 1, 2, 3, and 4, and the names are none, sub, up, average, and payoff. By the way, sub and up are directional. They're like directional relationships in relationship to the pixel you are targeting. So let's read this again, but we'll read each record. Type 0, name none. Record 2, type 1, name sub. Record 3, type is 2, name is up. Record 4, type is 3, name is average. And the 5th record, the type is 4, and the name is Paeth, or P-A-E-T-H. I could be pronouncing that wrong. It's like made by Andrew M. Paeth. That's who invented it. It's kind of a different type of average as far as I'm concerned from looking at the formula, where it's like, I think it's like A plus B minus C, and then you take whatever value is closest to that resulting calculation. Note that filter method 0 in IHDR specifies exactly this set of 5 filter types. If the set of filter types is ever extended, a different filter method number will be assigned to the extended set so that decoders need not compress the data to discover that it contains unsupported filter types. The encoder can choose which of these The encoder can choose which of these filter algorithms to apply on a scanline by scanline basis. In the image data sent to the compression step, each scanline is preceded by a filter type byte that specifies the filter algorithm for that scanline. End of page 31 of RFC-2083. Page 32, RFC-2083. Filtering algorithms are applied to bytes, not pixels. Regardless of the bit depth or color type of the image, the filtering algorithms work on the byte sequence formed by a scanline that has been represented as described in image layout section 2.3. If the image includes an alpha channel, the alpha data is filtered in the same way as the image data. When the image is interlaced, each pass of the interlaced pattern is treated as an independent image for filtering purposes. The filters work on the byte sequences formed by the pixels actually transmitted during a pass, and the previous scanline is the one previously transmitted in the same pass, not one adjacent in the complete image. Note that the sub-image transmitted in any one pass is always rectangular, but is of smaller width and/or height than the complete image. Filtering is not applied when this sub-image is empty. For all filters, the bytes to the left of the first pixel in a scanline must be treated as being 0. For filters that refer to the prior scanline, the entire prior scanline must be treated as being zeros for the first scanline of an image or of a pass of an interlaced image. To reverse the effect of a filter, the decoder must use the decoded values of the prior pixel on the same line, the pixel immediately above the current pixel on the prior line, and the pixel just to the left of the pixel above. This implies that at least one scanline's worth of image data will have to be stored by the decoder at all times. Even though some filter types do not refer to the prior scanline, the decoder will always need to store each scanline as it is decoded, since the next scanline might use a filter that refers to it. PNG imposes no restriction on which filter types can be applied to an image. However, the filters are not equally effective on all types of data. See recommendations for encoders, filter selection, section 9.6. See also rationale, filtering, section 12.9. 6.2, filter type 0, none. With the none filter, the scanline is transmitted unmodified. It is only necessary to insert a filter type byte before the data. End of page 32 of RFC 2083. 6.3, filter type 1 sub. The subfilter transmits the difference between each byte and the value of the corresponding byte of the prior level. To compute the subfilter, apply the following formula to each byte of the scanline. Sub invoke x equals raw invoke x minus raw invoke x minus BPP. Or sub with parameter x equals raw with parameter x minus raw with parameter x minus BPP. Where x ranges from 0 to the number of bytes representing the scanline minus 1, raw x refers to the raw data byte at the byte position in the scanline, and BPP is defined as the number of bytes per complete pixel, rounding up to 1. For example, for color type 2 with bit depth of 16, BPP is equal to 6, 3 samples, 2 bytes per sample. For color type 0 with a bit depth of 2, BPP is equal to 1, rounding up. For color type 4 with a bit depth of 16, BPP is equal to 4, 2 byte grayscale sample plus 2 byte alpha sample. Note this computation is done for each byte regardless of bit depth. In a 16-bit image, each MSB is predicted from the preceding MSB, and each LSB from the preceding LSB, because of the way that BPP is defined. Unsigned arithmetic modulo 256 is used so that both the inputs and outputs fit into bytes. The sequence of subvalues is transmitted as the filtered scanline. For all x less than 0, assume raw x equals 0. That kind of looks like flooring to me. Anyways, to reverse the effect of the subfilter after decompression, output the following value: sub x plus raw x minus BPP. Computed mod 256, where raw refers to the bytes already decoded. 6.4. Filter type 2 up. The up filter is just like the subfilter, except that the pixel immediately above the current pixel, rather than just to its left, is used as the predictor. To compute the up filter, apply the following formula to each byte of the scanline. Up x equals raw x minus prior x. End of page 33 of RFC-2083. Where x ranges from 0 to the number of bytes representing the scanline minus 1, raw x refers to the raw data byte at the byte position in the scanline. Prior x refers to the unfiltered bytes of the prior scanline. Note that this is done for each byte regardless of the bit depth. Unsigned arithmetic modulo 256 is used so that both the inputs and the outputs fit into bytes. The sequence of up values is transmitted as the unfiltered scanline. On the first scanline of the image, or of a pass of an interlaced image, assume prior x equals 0 for all x. To reverse the effect of the up filter after decompression, output the following value: up x plus prior x. Computed mod 256, where prior refers to the decoded bytes of the prior scanline. 6.5. Filter type 3 average. The average filter uses the average of two neighboring pixels left and above to predict the value of a pixel. To compute the average filter, apply the following formula to each byte of the scanline. Average x equals raw x minus floor, and we're flooring the following equation, which is open parentheses, raw with the parameters x minus BPP plus prior with the parameter x, close parentheses, divided by 2. And then another close parentheses, and that close parentheses is for the floor command. Where x ranges from 0 to the number of bytes representing the scanline minus 1, raw x refers to the raw data byte at that byte position in the scanline. Prior x refers to the unfiltered bytes of the prior scanline, and BPP is defined as for the subfilter. Note, this is done for each byte regardless of bit depth. The sequence of average values is transmitted as the filtered scanline. The subtraction of the predicted value from the new raw byte must be done modulo 256 so that both the inputs and outputs fit into bytes. However, the sum, raw, invoked with x minus BPP plus prior invoked with x, must be formed without overflow using at least 9-bit arithmetic. Floor function indicates that the result of the division is rounded to the next lower integer if fractional. In other words, it is an integer division or right shift operation. End of page 34 of RFC-2083. For all x less than 0, assume raw invoked with x equals 0 on the first scanline of an image, or of a pass of an interlaced image. Assume prior x equals 0 for all x. To reverse the effect of the average filter after decompression, output the following value: average x plus floor. Floor is taking the equation open parentheses raw invoked with x minus BPP plus prior invoked with x close parentheses, all divided by 2, and that's what's going into the floor function, and there's a close paren that is closing that. So let me just say all the characters instead of saying it like that, just one more time. Average open parentheses x close parentheses plus floor open paren raw open paren x minus BPP close paren plus prior open paren x close paren / 2 close paren, where the result is computed mod 256, but the prediction is calculated in the same way as for encoding. Raw refers to the bytes already decoded, and prior refers to the decoded bytes of the prior scan line. Filter type 4, paeth, P-A-E-T-H. The paeth filter computes a simple linear function of the 3 neighboring pixels left above upper left, and then chooses as predictor the neighboring pixel closest to the computed value. This technique is due to Alan W. Paeth. Oh, W. Paeth, not M. Paeth. I think I said, or maybe I said Andrew, but it's Alan W. Paeth, and there is a link. Let's see if we can hover over that really quick. Image compression made easy. So I don't know exactly where it's going. Let's open it up in a new tab really quick. Oh, it's just it's an internal link. Never mind. So it will be covered in this reading. To compute the paeth filter, apply the following formula to each byte of the scan line. Paeth x equals raw x minus paeth predictor, and then within this function we have raw invoked with x minus BPP, comma, prior invoked with x, comma, prior invoked with x minus BPP. So the paeth predictor is taking 3 parameters. I'm going to guess those are the different directional pixels, your up and your upper left and your left. Let's keep reading here. Where x ranges from 0 to the number of bytes, representing the scan line -1, raw x refers to the raw data byte at that byte position in the scan line, prior x refers to the unfiltered bytes of the prior scan line, and BPP is defined as for the subfilter. Note this is done for each byte regardless of the bit depth. Unsigned arithmetic modulo 256 is used so that both the inputs and the outputs fit into bytes. The sequence of paeth values is transmitted as the unfiltered scan line. End of page 35 of RFC-2083. We're on page 36 now. The paeth predictor function is defined by the following pseudocode. We have function paeth predictor taking parameters a, b, and c. And within the body of this function, denoted by a begin and end, we're starting with a semicolon. Not sure why. An empty statement. A equals left, B equals above, C equals upper left. So we got, we have 3 variable declarations, I think they're saying. So A is your left pixel, B is your above pixel, and C is your upper left. So P has a colon equal, so that is for declaration and assignment, from what I understand with pseudocode and from languages like Golang. P colon equals A plus B minus C. That is our initial estimate. PA assigned and equal to absolute value P minus A, distances to A, B, C. PB colon equals abs P minus A. PC colon equals abs P minus C. Oh, okay, so there's 2 comments here. I think that's what these semicolon starting lines are. Kind of like AutoHotkey does this, where comments are started by semicolons. Return nearest of ABC, breaking ties in order ABC. We have another statement. If PA is less than PB and PA is less than PC, then return A. Else, if PB is less than PC, then return B. Else, return C. And that is the entire body of the function. I can't really visualize that unless I draw it out, so we'll just keep on going. The calculations within the path predictor function must be performed exactly without overflow. Arithmetic modulo 256 is to be used only for the final step of subtracting the final result from the target byte value. Note that the order in which ties are broken is critical and must not be altered. The tie break order is pixel to the left, pixel above, pixel to the upper left. This order differs from that given in Path's article. Okay, so it says that basically the rules for the PNG Path algorithm are slightly different than the actual algorithm that the original author by the name of Path described. And tie breaks, I'm going to guess that that's when the differences are all equivalent. If the differences were all equivalent, or two differences are equivalent, the rules for how you are going to break those ties in order is pixel to the left, pixel above, and pixel to the upper left. For all x less than 0, assume raw x equals 0 and prior x equals 0 on the first scan line of an image or of a pass of an interlaced image. Assume prior x equals 0 for all x. To reverse the effect of path filter after decompression, output the following value: path x plus path predictor, invoked with 3 parameters. The first parameter is raw, invoked with x minus bp. Second parameter is prior, invoked with x. And the last and third parameter is prior, invoked with x minus bpp. Computed mod 256, where raw and prior refers to bytes already decoded. Exactly the same path predictor function is used by both encoder and decoder. 7. Chunk ordering rules. To allow new chunk types to be added to PNG, it is necessary to establish rules about the ordering requirements for all chunk types. Otherwise, a PNG editing program cannot know what to do when it encounters an unknown chunk. End of page 36 of RFC-2083, on to page 37. We define a PNG editor as a program that modifies a PNG file and wishes to preserve as much as possible of the ancillary information in the file. Two examples of PNG editors are a program that adds or modifies text chunks and a program that adds a suggested palette to a true color PNG file. Ordinary image editors are not PNG editors in this sense because they usually discard all unrecognized information while reading an image. Note, we strongly encourage programs handling PNG files to preserve ancillary information whenever possible. As an example of possible problems, consider a hypothetical new ancillary chunk type that is safe to copy and is required to appear after PLTE if PLTE is present. If our program to add a suggested PLTE does not recognize this new chunk, it may insert PLTE in the wrong place, namely after the new chunk. We could prevent such problems by requiring PNG editors to discard all unknown chunks, but that is a very unattractive solution. Instead, PNG requires ancillary chunks not to have ordering restrictions like this. To prevent this type of problem while allowing for future extension, we put some constraints on both the behavior of PNG editors and the allowed ordering requirements for chunks. 7.1 Behavior of PNG editors. The rules for PNG editors are: bullet point. When copying an unknown, unsafe to copy ancillary chunk, a PNG editor must not move the chunk relative to any critical chunk. It can relocate the chunk freely relative to other ancillary chunks that occur between the same pair of critical chunks. This is well defined since the editor must not add, delete, modify, or reorder critical chunks if it is preserving unknown, unsafe to copy chunks. Bullet point. When copying an unknown, safe to copy ancillary chunk, a PNG editor must not move the chunk from before IDAT to after IDAT or vice versa. This is well defined because IDAT is always present. Any other reordering is permitted. When copying a known ancillary chunk type, an editor need only honor the specific chunk ordering rules that exist for that chunk type. However, it can always choose to apply the above general rules instead. Bullet point. PNG editors must give up on encountering an unknown critical chunk type because there is no way to be certain that a valid file will result from modifying a file containing such a chunk. Note that simply discarding the chunk is not good enough because it might have unknown implications for the interpretation of other chunks. End of page 37 of RFC 2083. These rules are expressed in terms of copying chunks from an input file to an output file, but they apply in the obvious way if a PNG file is modified in place. See also Chunk Naming Conventions, Section 3.3. 7.2 Ordering of Ancillary Chunks. The ordering rules for ancillary chunk type cannot be any stricter than this. Bullet point. Unsafe to copy chunks can have ordering requirements relative to critical chunks. Safe to copy chunks can have ordering requirements relative to IDAT. The actual ordering rules for any The actual ordering rules for any particular ancillary chunk type may be weaker. See, for example, the ordering rules for the standard ancillary chunk types, Summary of Standard Chunks, Section 4.3. Decoders must not assume more about the positioning of any ancillary chunk than is specified by the chunk ordering rules. In particular, it is never valid to assume that a specific ancillary chunk type occurs within any particular positioning relative to other ancillary chunks. For example, it is unsafe to assume that your private ancillary chunk occurs immediately before IEND, even if your application always writes it there. A PNG editor might have inserted some ancillary chunk after it, but you can safely assume that your chunk will remain somewhere between IDAT and IEND. 7.3 Ordering of Critical Chunks. Critical chunks can have arbitrary ordering requirements because PNG editors are required to give up if they encounter unknown critical chunks. For example, IHDR has the special ordering rule that it must always appear first. A PNG editor, or indeed any PNG writing program, must know how to follow the ordering rules for any critical chunk type that it can emit. End of page 38 of RFC 2083. We're on page 39. 8. Section 8. Miscellaneous Topics. 8.1. File name extension. On systems where file names customarily include an extension signifying file type, the extension .png is recommended for PNG files. Lowercase .png is preferred if the file names are case sensitive. 8.2 Internet Media Type. The Internet Assigned Numbers Authority, IANA, has registered image/PNG as the Internet Media Type for the PNG RFC-2045, RFC-2048. For robustness, decoders may choose to support the interim media type image/x-PNG, which was in use before the registration was complete. 8.3 Macintosh File Layout. In the Apple Macintosh system, the following conventions are recommended. The 4-byte file type code for PNG files is PNGF. So that is within quotations, capital P, capital N, capital G, lowercase f. This code has been registered with Apple for PNG files. The creator code will vary depending on the creating application. So, file type code. So that almost sounds like, so is that stored in the actual file's binary? Or is that an extension? I don't know. I don't really use Macintoshes. So it'd be good to look up what file type code is. So I'm going to pause here and look that up really quick. Alright, so I'm not sure exactly where creator code is stored, but it is a 4-byte value that is typically ASCII. And it kind of lets you know what application made the file, and it also creates a file association, like which program to open that file with. So instead of like having a file extension, and that file extension always opens with a certain program, the creator code can give a little bit more variation to that. So we can see a little screenshot here, and it says same type, different creators, Depeche Mode, Precious.mp3, and we see a different icon, so it's opening with a different program than Cars, you might think, also mp3, and then another program, but they're all mp3s. Let's look at the caption here. The creator code is responsible for linking the file and the program that will launch when the file is double-clicked. This Mac OS window show 4 files of the same type code, mp3, but with 4 different creator codes: Auden, Audion, Hook, iTunes, SCPL, Sound App, and NSWA, and that's Winamp. NSWA is Winamp? Oh, whatever. Okay, so now that we know what that means, let me just read this again. The 4-byte file type code for PNG files is PNGF. This code has been registered with Apple for PNG files. The creator code will vary depending on the creating application. The contents of the data fork must be a PNG file exactly as described in the rest of this application. The contents of the resource fork are unspecified. It may be empty or may contain application-dependent resources. When transferring a Macintosh PNG file to a non-Macintosh system, only the data fork should be transferred. 8.4 Multiple Image Extension. PNG itself is strictly a single image format, however, it may be necessary to store multiple images within one file. For example, this is needed to convert some GIF files. In the future, a multiple image format based on PNG may be defined. Such a format will be considered a separate file format and will have a different signature. PNG supporting applications may or may not choose to support the multiple image format. See rationale, why not these features, section 12.3, end of page 39. We're on RFC-2083, now on page 40 of RFC-2083. Section 8.5, security considerations. A PNG file or data stream is composed of a collection of explicitly typed chunks. Chunks whose contents are defined by the specification code. Sorry, I said that totally wrong. We're going to do this over again. 8.5 Security considerations. A PNG file or data stream is composed of a collection of explicitly typed chunks. Chunks whose contents are defined by the specification could actually contain anything, including malicious code. But there is no known risk that such malicious code could be executed on the recipient's computer as a result of decoding the PNG image. I have an idea. So the deflate algorithm needs to know the final size of the uncompressed data, and the IHDR chunk tells us the width and height of the image. So if you made a malicious IHDR chunk that said that the final image was like 4 by 4 pixels, but it was actually like a 64 by 64-bit 4-pixel image, right? So the actual data is a lot more. Then you could probably create some type of buffer overflow attack, just from what I've been reading. I don't know the exact implementations, but I don't know. I definitely see an opportunity here to make a buffer overflow attack by giving an incorrect header for the size of the uncompressed data. Just from what I've looked at with the deflate algorithm, but that's just a hunch. But let's, I don't know how you would implement it. It's just a hunch. And if I have a hunch, I'm sure there's a way you could do it. So I don't know when they say no security concerns that they know of. I don't know if they mean no explicit implementations or, we don't even have a hunch of how something bad could be done. But, maybe I'm just, spewing bullshit. I don't know. But I definitely... I don't know. Whatever. Let's keep reading. The possible security risks associated with future chunk types cannot be specified at this time. Security issues will be considered when evaluating chunks proposed for registration as public chunks. There is no additional security risk associated with unknown or unimplemented chunk types because such chunks will be ignored or at most be copied into another PNG file. The text and ZTXT chunks contain data that is meant to be displayed as plain text. It is possible that if the decoder displays such text without filtering out control characters, especially the ESC escape character, certain systems or terminals could behave in undesirable and unsecure ways. We recommend that decoders filter out control characters to avoid these risks. See recommendations for decoders text chunk processing, section 10.11. So that almost sounds like a SQL injection kind of style attack, right? Where you You just insert characters that they're not expecting for, and if you don't sanitize the data, then bad things happen. That's kind of what that sounds like. Because every chunk's length is available at its beginning, and because every chunk has a CRC trailer, there is a very robust defense against corrupted data and against fraudulent chunks that attempt to overflow the decoder's buffers. Also, the PNG signature bytes provide early detection of common file transmission errors. Okay, so I see what they're saying. Previously, when I was talking about a buffer overflow attack, they're saying that that won't be a problem because we have these checksums. So as long as your PNG editor or your PNG opener, your PNG compressor, decompressor, whatever you want to call that, as long as your PNG library is correctly written to the spec, you should be relatively safe from buffer overflows. That's what I'm reading. A decoder that fails to check CRCs could be subject to data corruption. The only likely consequence of such corruption is incorrectly displayed pixels within the image. Worse things might happen if the CRC of the IHDR chunk is not checked and the width or height fields are corrupted. See recommendations for decoders, error checking, section 10.1. So this is exactly what I was speculating about earlier, where if you say that the image is 2 by 2 pixels, but there's actually 64 by 64 pixels worth of data, you could create some type of buffer overflow attack. A poorly written chunk decoder might be subject to buffer overflow because chunks can be extremely large, up to 2 to the power of 31 minus bytes long. But properly written decoders will handle large chunks without difficulty. That is the end of page 40. We are reading RFC-2083, PNG, Portable Network Graphics, March 1997. We are on page 41, section 9, recommendations for encoders. Section 9, recommendations for encoders. This chapter gives some recommendations for encoder behavior. The only absolute requirement on PNG encoder is that it produce files that conform to the format specified in the preceding chapters. However, the best results will usually be achieved by following these recommendations. 9.1 Sample depth scaling. When encoding input samples that have a sample depth that cannot be directly represented in PNG, the encoder must scale the samples up to a sample depth that is allowed by PNG. So we're going to round up. The most accurate scaling method is the linear equation. Output equals round, input multiplied by max out sample divided by max in sample. Where the input sample range from 0 to max in sample, and the output range from 0 to max out sample, which is 2 to the power of sample depth minus 1. A close approximation to the linear scaling method can be achieved by left bit replication, which is shifting the valid bits to begin in the most significant bit and repeating the most significant bits into the open bits. This method is often faster to compute than linear scaling. As an example, assume that 5-bit samples are being scaled up 8 bits. If the source sample value is 27 in the range from 0 to 31, then the original bits are 4, 2, 1, 10, and 0. Okay, so those are the bit values on the top. And then we have 1, 1, 0, 1, 1. Left bit replication gives a value of 222. So let me... Okay, there we go. So we have the bit indices 0 to 7 on the top, it looks like. The original bits, the 1, 1, 0, 1, 1, all the way to the left. And our leftmost bits repeated to fill open bits. We have a 1, 1, and a 0. So I guess duplicate a whole bunch of 1s and then make the first bit 0. That's what's going on there? I'm not quite sure. Which matches the value computed by the linear equation. Left bit replication usually gives the same value as linear scaling and is never off by more than 1. End of page 41 of RFC 2083, on to page 42. A distinctly less accurate approximation is obtained by simply left-shifting the input value and filling the low-order bits with zeros. This scheme cannot reproduce white exactly since it does not generate an all-ones maximum value. The net effect is to darken the image slightly. This method is not recommended in general, but it does have the effect of improving compression, particularly when dealing with greater than 8-bit sample depths. Since the relative error introduced by zero fill scaling is small at high sample depths, some encoders may choose to use it. Zero fill must not be used for alpha channel data. However, since many decoders will special case alpha values of all zeros and all ones, it is important to represent both these values exactly in the scale data. So that kind of sounds like why Macromedia Flash always makes it so when I load a PNG file, I can never get 255 for any of my channel values because they're all off by 1. That sounds like where that problem originated from. I could be making things up here. I'm going to stop the recording just so I can make a note of this. Alright. When the encoder writes an S-bit chunk, it is required to do the scaling in such a way that the high-order bits of the stored samples match the original data. That is, if the S-bit chunk specifies a sample depth of S, the high-order S-bits of the stored data must agree with the original S-bit data values. This allows decoders to recover the original data by shifting right. The added low-order bits are not constrained. Note that all the above scaling methods meet this restriction. When scaling up source data, it is recommended that the low-order bits be filled consistently for all samples. That is, the same source value should generate the same sample value at any pixel position. This improves compression by reducing the number of distinct sample values. However, this is not a requirement, and some encoders may choose not to follow it. For example, an encoder might instead dither the low-order bits, improving displayed image quality at the price of increasing file size. Increasing file size, hold on. There we go. In some applications, the original source data may have a range that is not a power of 2. The linear scaling equation still works for this case, although the shifting methods do not. It is recommended that an S-bit chunk not be written for such images, since S-bit suggests that the original data range was exactly 0.2 to the power of S minus 1. 9.2 Encoder Gamma Handling. See Gamma Tutorial Chapter 13 if you aren't already familiar with the gamma issues. Proper handling of gamma encoded with the gamma chunk is an encoder... Sorry, let me reread that. Proper handling of a gamma encoding and a gamma chunk in an encoder depends on the prior history of the sample values and on whether these values have already been quantized to integers. End of page 42 of RFC-2083, PNG Portable Network Graphics, March 1997. We are on page 43. If the encoder has access to sample intensity values in a floating point or high-precision integer form, perhaps from a computer image renderer, then it is recommended that the encoder perform its own gamma encoding before quantizing the data to integer values for storage in the file. Applying gamma encoding at this stage results in images with fewer banding artifacts at a given sample depth, or allows similar samples while retaining the same visual quality. A linear intensity level expressed as a floating point value in the range 0 to 1 can be converted to gamma encoded sample value by sample equals round, open paren, parenthesis to the power of encoder underscore gamma, close paren, multiplied by max sample, close paren. The file gamma value to be written in the PNG gamma chunk is the same as encoder gamma in this equation. Since we are assuming the initial intensity value is linear, in effect, the camera gamma is 1.0. If the image is being written to a file only, the encoder gamma can be selected somewhat arbitrarily. Values of 0.45 or 0.5 are generally good choices because they are common in video systems, and so most PNG decoders would do a good job displaying such images. Some image renderers may simultaneously write the image to a PNG file and display it on screen. The displayed pixels should be gamma corrected for the display system and viewing conditions in use so that the user sees a proper representation of the intended scene. An appropriate gamma correction value is screen_GC equals viewing_gamma divided by display gamma. In more proper English, screen GC equals viewing gamma divided by display gamma. If the renderer wants to write the same gamma-corrected sample values to the PNG file, avoiding a separate gamma encoding step for file output, then this screen GC value should be written in the gamma chunk. This allows a PNG decoder to reproduce what the file's originator saw on a screen This allows a PNG decoder to reproduce what the file's originator saw on screen during rendering, provided the decoder properly supports arbitrary values in a gamma chunk. However, it is equally reasonable for a renderer to apply gamma correction for screen display using a gamma appropriate to the viewing conditions, and to separately gamma encode the sample values for file storage using a standard value of gamma, such as 0.5. In fact, this is preferable since some PNG decoders may not accurately display images with unusual gamma values. End of page 43 of RFC-2083. Top of page 44. Computer graphics renderers often do not perform gamma encoding, instead making sample values directly proportional to scene light intensity. If the PNG encoder receives sample values that have already been quantized into linear light integer values, there is no point in doing gamma encoding on them. That would just result in further loss of information. The encoder should just write the sample values to the PNG file. This linear sample encoding is equivalent to gamma encoding with a gamma of 1.0, so graphics programs that produce linear samples should always emit a gamma chunk specifying a gamma of 1.0. When the sample values come directly from a piece of hardware, the correct gamma value is determined by the gamma characteristics of the hardware. In the case of video digitizers, frame grabbers, gamma should be 0.45 or 0.5 for NTSC, possibly less for PAL or SECAM, since video camera transfer functions are standardized. Image scanners are less predictable. Their output samples may be linear, gamma 1.0, since CCD sensors themselves are linear, or the scanner hardware may have already applied gamma correction designed to compensate for dot grain and subsequent printing, gamma of about 0.57, or the scanner may have corrected the samples for display on a CRT, gamma of 0.4 to 0.5. You will need to refer to the scanner's manual or even scan a calibrated gray wedge to determine what a particular scanner does. File format converters generally should not attempt to convert supplied images to a different gamma. Store the data in the PNG file without conversion and record the source gamma if it is known. Gamma alteration at file conversion time causes requantization of the set of intensity levels that are represented, introducing further round-off error with little benefit. It's almost always better to just copy the sample values intact from the input to the output file. Yeah, I feel like you could get some generation loss doing that. In some cases, the supplied image may be in an image format, e.g. TIFF, that can describe the gamma characteristics of the image. In such cases, a file format converter is strongly encouraged to write a PNG gamma chunk that corresponds to the known gamma of the source image. Note that some file formats specify the gamma of the display system, not the camera. If the input file's gamma value is greater than 1.0, it is almost certainly a display system gamma, and you should use its reciprocal for the PNG gamma. And that is the end of page 44 of RFC 2083. We are at the top of page 45. If the encoder or file format converter does not know how an image was originally created, but does know that the image has been displayed satisfactorily on the display with gamma display gamma under lighting conditions that were Let me just reread this paragraph. The variables make this very weird to read, so I don't expect the words that come next. If the encoder or file format converter does not know how an image was originally created, but does know that the image has been displayed satisfactorily on a display with gamma variable display underscore gamma under lighting conditions where a particular variable viewing underscore gamma is appropriate, then the image can be marked as having the variable file underscore gamma. And then we have a formula, file underscore gamma equals viewing underscore gamma divided by display underscore gamma. This will allow viewers of the PNG file to see the same image that the person running the file format converter saw, although this may not be precisely the correct value of the image gamma. It's better to write a gamma chunk with an appropriately right value than omit the chunk and force PNG decoders to guess at an appropriate gamma. On the other hand, if the image file is being converted as part of a bulk conversion with no one looking at each image, then it is better to omit the gamma chunk entirely. If the image gamma has to be guessed at, leave it to the decoder to do the guessing. Gamma does not apply to alpha samples. Alpha is always represented linearly. See also Recommendations for Decoders, Decoder Gamma Handling, Section 10.5. 9.3 Encoder Color Handling. See Color Tutorial, Chapter 14 if you aren't already familiar with color issues. If it is possible for the encoder to determine the chromatities of the source display primaries or to make a strong guess based on the origin of the image or the hardware running it, then the encoder is strongly encouraged to output the CHRM chunk. If it does so, the gamma chunk should also be written. Decoders can do little with the CHRM if gamma is missing. And that's the end of page 45. We are on page 46 of RFC-2083, PNG Portable Network Graphics, March 1997. Video created with recent video equipment probably uses the CCIR 709 primaries and D65 white point. And there's a reference marker here, ITU-BT709, which are, and we have a table. It has two records that are labeled X and Y, and then we have columns R, G, B, and white. So the first record, the X value is 0.640, G 0.300, B 0.150, white 0.3127. The Y record, we have red 0.330, G 0.600, B is 0.060, and white is 0.3290. An older, but still very popular video standard is SMPTE-C. There's a reference here that looks like they forgot the hyperlink, SMPTE-170M. We have two records, once again, labeled X and Y with RGB and white columns. The X record is R 0.630, G 0.310, B 0.155, white 0.3127. The Y record, red is 0.340, G 0.595, B 0.070, and white 0.3290. The original NTSC color primaries have not been used in decades, although you may still find the NTSC numbers listed in standards documents. You won't find any images that actually use them. Scanners that produce PNG files as output should insert a filter chromatities into a CHRM chunk and the camera underscore gamma into a gamma chunk. In the case of hand-drawn or digitally edited images, you have to determine what monitor they were viewed on when being produced. Many image editing programs allow you to specify what type of monitor you are using. This is often because they are working in some device-independent space internally. Such programs have enough information to write valid CHRM and gamma chunks. and should do so automatically. If the encoder is compiled as a portion of a computer image renderer that performs full spectral rendering, the monitor values that were used to convert from the internal device-independent color space to RGB should be written into the CHR chunk. Any colors that are outside the gamut of the chosen RGB device should be clipped or otherwise constrained to be within the gamut. PNG does not store out-of-gamut colors. If the computer image renderer performs calculations directly in device-dependent RGB space, a CHRM chunk should not be written unless the scene description and rendering parameters have been adjusted to look good on a particular monitor. In that case, the data for that monitor, if known, should be used to construct a CHRM chunk. End of page 46 of RFC-2083 PNG Portable Network Graphics. We are at the top of page 47. There are often cases where an image's exact origins are unknown, particularly if it began life in some other format. A few image formats store calibration information, which can be used to fill in the CHRM chunk. For example, all photo CD images use the CCIR 709 primaries and D65 white point, so these values can be written into the CHRM chunk when converting a photo CD file. Photo CD also uses the SMPTE-170M transfer function, which is closely approximated by a gamma of 0.5. Photo CD can store colors outside the RGB gamut, so the image data will require gamut mapping before writing to PNG format. TIFF 6.0 files can optionally store calibration information, which, if present, should be used to construct the CHRM chunk. GIF and most other formats do not store any calibration information. It is not recommended that file format converters attempt to convert supplied images to a different RGB color space. Store the data in the PNG file without conversion and record the source primary chromatities if they are known. Color space transformation at file conversion time is a bad idea because of gamut mismatches and rounding errors. As with gamma conversions, it's better to store the data losslessly and incur at most one conversion when the image is finally displayed. See also recommendations for decoders, decoder color handling, section 10.6, 9.4 alpha channel creation. The alpha channel can be regarded either as a mask that temporarily hides transparent parts of the image or as a means for constructing a non-rectangular image. In the first case, the color values of fully transparent pixels should be preserved for future use. In the second case, the transparent pixels carry no useful data and are simply there to fill out the rectangular image areas required by PNG. In this case, fully transparent pixels should all be assigned the same color value for best compression. Image authors should keep in mind the possibility that a decoder will ignore the transparency control. Hence, the colors assigned to transparent pixels should be reasonable background colors whenever feasible. For applications that do not require a full alpha channel or cannot afford the price in compression efficiency, the TRNS transparency chunk is also available. End of page 47 of RFC 2083, top of page 48. If the image has a known background color, this color should be written in the BKGD chunk, lowercase b, capital K, capital G, capital D. Even decoders that ignore transparency may use the BKGD color to fill unused screen area. If the original image has pre-multiplied, also called associated alpha data, convert it to PNG's non-pre-multiplied format by dividing each sample value by the corresponding alpha value, then multiplying by the maximum value for the image bit depth, and rounding to the nearest integer. In valid pre-multiplied data, the sample values never exceed their corresponding alpha values, so the result of the division should always be in the range 0 to 1. If the alpha value is 0, output black zeros. 9.5. Oh, also, I wonder if that pre-multiplied alpha thing is also the reason why I see weird things with PNG and Macromedia Flash. Which maybe I should get over, because Flash is dead. Anyways, 9.5. Suggested palettes. A PLTE chunk can appear in true-color PNG files. In such files, the chunk is not an essential part of the image data, but simply represents a suggested palette that viewers may use to present the image on index color display hardware. A suggested palette is of no interest to viewers running on true color hardware. If an encoder chooses to provide a suggested palette, it is recommended that a HIST chunk also be written to indicate the relative importance of the palette entries. The histogram values are most easily computed as nearest neighbor counts, that is, the approximate usage of each palette entry if no dithering is applied. These counts will often be applied for free as a consequence of developing the suggested palette. For images of color type 2, true color without alpha channel, it is recommended that the palette and histogram be computed with reference to the RGB data only, ignoring any transparent color specification. If the file uses transparency, has a TRNS chunk, viewers can easily adapt the resulting palette for use with their intended background color. They need only replace the palette entry closest to the TRNS color with their background color, which may or may not match the file's BKGD color, if any. For images of color type 6, true color with alpha channel, it is recommended that a BKGD chunk appear and that the palette and histogram be computed with reference to the image as it would appear after compositing against the specified background color. This definition is necessary to ensure that useful palette entries are generated for pixels having fractional alpha values. The resulting palette will probably only be useful to viewers that present the image against the same background color. It is recommended that PNG editors delete or recompute palette if they alter or remove the BKGD chunk in an image of color type 6. End of page 48 of RFC-2083 onto page 49. If PLTE appears without BKGD in an image color of type 6, the circumstances under which the palette was computed are unspecified. 9.6. Filter selection for images of color type 3, index color with filter type 0, none. It is usually the most effective. Note that color images with 256 or fewer core colors should almost always be stored in index color format. True color format is likely to be much larger. Filter type 0 is also recommended for images of bit depths less than 8. For low bit depth grayscale images, it may be a net win to expand the image to 8-bit representation and apply filtering, but this is rare. For true color and grayscale images, any of the 5 filters may prove the most effective. If an encoder uses a fixed filter, the payoff filter is most likely to be the best. For best compression of true color and grayscale images, we recommend an adaptive filtering approach in which a filter is chosen for each scanline. The following simple heuristic has performed well in early tests. Compute the output scanline using all 5 filters and select the filter that gives the smallest sum of absolute values of outputs. Consider the output bytes as signed differences for this test. This method usually outperforms any single fixed filter choice. However, it is likely that much better heuristics will be found as more experience is gained with PNG. Filtering according to these recommendations is effective on interlaced as well as non-interlaced images. 9.7. Text chunk processing. 9.7 Text chunk processing. 9.7 Text chunk processing. A non-empty keyword must be provided for each text chunk. The generic keyword comment can be used if no better description of the text is available. If a user-supplied keyword is used, be sure to check that it meets the restrictions on keywords. PNG text strings are expected to use Latin 1 character set. Encoders should avoid storing characters that are not defined in Latin 1 and should provide character code remapping if the local system's character set is not Latin 1. Encoders should discourage the creation of single lines of text longer than 79 characters in order to facilitate easy reading. End of page 49. top of page 50 of RFC-2083, it is recommended that text items less than 1K, 1024 bytes in size should not be output using uncompressed TEXT chunks. In particular, it is recommended that the basic title and author keywords should always be output using uncompressed TEXT chunks. Lengthy disclaimers, on the other hand, are ideal candidates for ZTXT. Placing large text and ZTXT chunks after the image data, after IDAT, can speed up image display in some situations since the decoder won't have to read over the text to get to the image data. But it is recommended that small text chunks, such as the image title, appear before IDAT. 9.8 Use of private chunks. Applications can use PNG private chunks to carry information that need not be understood by other applications. Such chunks can be given names with lowercase second letters to ensure that they can never conflict with any future public chunk definition. Note, however, that there's no guarantee that some other application will not use the same private chunk name. If you use a private chunk type, it is prudent to store additional identifying information at the beginning of the chunk data. So I'm guessing, additional information to avoid collisions with other people using the same chunk name is what they're saying. Use an ancillary chunk type, lowercase first letter, not a critical chunk type, for all private chunks that store information that is not absolutely essential to view the image. Creation of private critical chunks is discouraged because they render PNG files unportable. Such chunks should not be used in publicly available software or files. If private critical chunks are essential for your application, it is recommended that one appear near the start of the file so that a standard decoder need not read very far before discovering that it cannot handle the file. If you want others outside your organization to understand a chunk type that you invent, contact maintainers of the PNG specification to submit a proposed chunk name and definition for addition to the list of special purpose public chunks. See Additional Chunk Types, section 4.4. Note that a proposed public chunk name with uppercase second letter must not be used in publicly available software files until registration has been approved. If ancillary chunks contain textual information that might be of interest to a human user, you should not create a special chunk type for it. Instead, use a TEXT chunk and define a suitable keyword. That way, the information will be available to users not using your software. End of page 50, on to page 51 of RFC 2083. Keywords and TEXT chunks should be reasonably self-explanatory, since the idea is to let others users figure out what the chunk contains. If of general usefulness, new keywords can be registered with the maintainers of the PNG specification, but it is permissible to use keywords without registering them first. 9.9 Private Type and Method Codes. This specification defines the meaning of only some of the possible values of some fields. For example, only compression method 0 and filter types 0 through 4 are defined. Numbers greater than 127 must be used when inventing experimental or private definitions of values for any of these fields. Numbers below 128 are reserved for possible future public extensions of this specification. Note that use of private type codes may render a file unreadable by standard decoders. Such codes are strongly discouraged except for experimental purposes and should not appear in publicly available software or files. Section 10, Recommendations for Decoders. This chapter gives some recommendations for decoder behavior. The only absolute requirement on a PNG decoder is that it successfully read any file conforming to the format specified in the preceding chapters. However, best results will usually be achieved by following these recommendations. Error checking. 10.1 Error checking. To ensure early detection of common file transfer problems, decoders should verify that all 8 bytes of the PNG signature are correct. See Rationale, PNG File Signatures, section 12.11. A decoder can have additional confidence in the file's integrity if the next 8 bytes are an IHDR chunk header with the correct chunk length. Unknown chunk types must be handled as described in Chunk Naming Conventions, Section 3.3, and unknown chunk type is not to be treated as an error unless it is a critical chunk. It is strongly recommended that decoders should verify the CRC on each chunk. In some situations, it is desirable to check the chunk header's length and type code before reading the chunk data and CRC. The chunk type can be checked for plausibility by seeking whether all 4 bytes are ASCII letters codes 65 to 90 and 97 to 122. Note that this need only be done for unrecognized type codes. If the total file, end of page 51 on page 52 of RFC-2083, I'm going to say that again, the sentence. If the total file size is known from the file system information, HTTP protocol, etc., the chunk length can be checked for plausibility as well. If CRCs are, I believe CRC is the chunk type, so that's not a pluralization. That's actually the lowercase s for the checksum chunk type. So if CRCS are not checked, dropped/added data bytes, or an erroneous chunk length can cause the decoder to get out of step and misinterpret subsequent data as a chunk header. Verifying that the chunk type contains letters is an inexpensive way of providing early error detection in this situation. For known length chunks, such as IHDR, decoders should treat an unexpected chunk length as an error. Further extensions to the specification will not add new fields to existing chunks. Instead, new chunk types will be added to carry new information. Unexpected values in fields of known chunks, for example, an unexpected compression method in the IHDR chunk, must be checked for and treated as errors. However, it is recommended that unexpected field values be treated as fatal errors only in critical chunks. An unexpected value in an ancillary chunk can be handled by ignoring the whole chunk as though it were an unknown chunk type. This recommendation assumes that the chunk's CRC has been verified. In decoders that do not check CRCs, it is safer to treat any unexpected value as indicating a corrupted file. 10.2 Pixel Dimensions. Non-square pixels can be represented, see the PHYS chunk, but viewers are not required to account for them. A viewer can present any PNG file as though its pixels are square. Conversely, viewers running on display hardware with non-square pixels are strongly encouraged to rescale images for proper display. 10.3 True Color Image Handling. To achieve PNG's goal of universal interchangeability, decoders are required to accept all types of PNG image, index color, true color, and grayscale. Viewers running on index color display hardware need to be able to reduce true color images to indexed format for viewing. This process is usually called color quantization. End of page 52, on to page 53 of RFC-2083, PNG Portable Network Graphics, March 1997. A simple, fast way of doing this is to reduce the image to a fixed palette. Palettes of uniform color spacing, color cubes, are usually used to minimize the per-pixel computation for photograph-like images. Dithering is recommended to avoid ugly contours in what should be smooth gradients. However, dithering introduces graininess that can be objectionable. The quality of rendering can be improved substantially by using a palette chosen specifically for the image, since a color cube usually has numerous entries that are unused in any particular image. This approach requires more work, first in choosing the palette, and second in mapping individual pixels to the closest available color. PNG allows the encoder to supply a suggested palette in a PLTE chunk, but not all encoders will do so, and the suggested palette may be unsuitable in any case. It may have too many or too few colors. High-quality viewers will therefore need to have a palette selection routine at hand. A large lookup table is usually the most feasible way of mapping individual pixels to palette entries with adequate speed. Numerous implementations of color quantization are available. The PNG reference implementation, libpng, includes code for the purpose. 10.4 Sample Depth Rescaling. Decoders may wish to scale PNG data to a lesser sample depth data precision for display. For example, 16-bit data will need to be reduced to 8-bit depth for use on most present-day display hardware. Reduction of 8-bit data to 5-bit depth is also common. The most accurate scaling is achieved by the linear equation output equals round input multiplied by max out sample divided by max in sample, where max in sample equals 2 to the power of sample depth minus 1, max out sample equals 2 to the power of desired sample depth minus 1. A slightly less accurate conversion is achieved by simply shifting right by sample depth minus desired sample depth places. For example, to reduce 16-bit samples to 8-bit, one need only discard the low-order byte. In many situations, the shift method is sufficiently accurate for display purposes, and it is certainly much faster. But if gamma correction is being done, sample rescaling can be merged into the gamma correction lookup table, as is illustrated in Decoder Gamma Handling, section 10.5. End of page 53, on to page 54 of RFC-2083. When an S-bit chunk is present, the original pre-PNG data can be recovered by shifting right to the sample depth specified by S-bit. Note that linear scaling will not necessarily reproduce the original data because the encoder is not required to have used linear scaling to scale up the data. However, the encoder is required to have used a method that preserves the high-order bits, so shifting always works. This is the only case in which shifting might be said to be more accurate than linear scaling. When comparing pixel values to TRNS chunk values to detect transparent pixels, it is necessary to do the comparison exactly. Therefore, transparent pixel detection must be done before reducing sample precision. 10.5 Decoder Gamma Handling. See Gamma Tutorial, Chapter 13 if you aren't already familiar with gamma issues. To produce correct tone reproduction, a good image display program should take into account the gammas of the image file and the display device, as well as the viewing gamma appropriate to the lighting conditions near the display. This can be done by calculating G bright equals in sample divided by max in sample, B bright equals G bright to the power of 1.0 divided by file gamma, V bright equals bright to the power of viewing gamma, GC video equals V bright to the power of 1.0 divided by display gamma, FB val equals round, GC video times max FB val, where max in sample is the maximum sample value in the file 255 for 8-bit, 65535 for 16-bit, etc. Max FB val is the maximum value of a frame buffer sample, 255 for 8-bit, 31 for 5-bit, etc. In sample is the value of the sample in the PNG file, and FB val is the value to write into the frame buffer. The first line converts from integer samples into a normalized 0 to 1 floating point value. The second undoes the gamma encoding of the image file to produce a linear intensity value. The third adjusts for the viewing conditions, and the fourth corrects for the display's system gamma value, and the fifth converts to an integer frame buffer sample. In practice, the second through fourth lines can be merged into GC video equals G bright to the power of, and then all in parentheses, viewing gamma divided by, all in parentheses, file gamma multiplied by display gamma, and then there's two closing parentheses. So as to perform only one power calculation for color images, the entire calculation is performed separately for R, G, and B values. End of page 54 of RFC 2083, on to page 55. It is not necessary to perform transcendental math for every pixel. Instead, compute a lookup table that gives the correct output value for every possible sample value. This requires only 256 calculations per image for 8-bit accuracy, not 1 or 3 calculations per pixel. For an index color image, a one-time correction of the palette is sufficient unless the image uses transparency and is being displayed against a non-uniform background. In some cases, even the cost of computing a gamma lookup table may be concerned. In these cases, viewers are encouraged to have pre-computed gamma correction tables for file gamma values of 1.0 and 0.5 with some reasonable choice of viewing underscore gamma and display underscore gamma, and to use the table closest to the gamma indicated in the file. This will produce acceptable results for the majority of real files. When the incoming image has unknown gamma, no gamma chunk, choose a likely default file gamma value, but allow the user to select a new one if the result proves too dark or too light. In practice, it is often difficult to determine what value of display gamma should be used. In systems with no built-in gamma correction, the display gamma is determined entirely by the CRT. Assuming a CRT underscore gamma of 2.5 is recommended, unless you have detailed calibration measurements of this particular CRT available. However, many modern frame buffers have lookup tables that are used to perform gamma correction, and on these systems, the display gamma value should be the gamma of the lookup table and CRT combined. You may not be able to find out what the lookup table contains from within an image viewer application, so you may have to ask the user what the system's gamma value is. Unfortunately, different manufacturers use different ways of specifying what should go into the lookup table, so interpretation of the system gamma value is system dependent. Gamma Tutorial Chapter 13 gives some examples. The response of real displays is actually more complex and can be described by a single number, display underscore gamma. If actual measurements of the monitor's light output as a function of voltage input are available, the fourth and fifth lines of the computation above can be replaced by a lookup in these measurements to find the actual frame buffer value that most nearly gives the desired brightness. End of page 55, onto the top of page 56, RFC-2083. The value of viewing gamma depends on the lighting conditions. See Gamma Tutorial Chapter 13 for more detail. Ideally, a viewer would allow the user to specify viewing gamma either directly, numerically, or via selecting from bright surround, dim surround, or dark surround conditions. Viewers that don't want to do this should just assume the value for viewing gamma of 1.0, since most computer displays live in brightly lit rooms. When viewing images that are digitized from video or that are destined to become video frames, the user might want to set the viewing gamma to about 1.25 regardless of the actual level of room lighting. This value of viewing gamma is built into NTSC video practice, and displaying an image with that viewing gamma allows the user to see what a TV set would show under the current room lighting conditions. This is not the same thing as trying to obtain the most accurate rendition of the content of the scene, which would require adjusting viewing gamma to correspond to the room lighting level. This is another reason viewers might want to allow users to adjust viewing gamma directly. 10.6 Decoder Color Handling. See Color Tutorial Chapter 14 if you aren't already familiar with issues. In many cases, decoders will treat image data in PNG files as device-dependent RGB data and display it without modification except for appropriate gamma correction. This provides the fastest display of PNG images. But unless the viewer uses exactly the same display hardware as the original image author used, the colors will not be exactly the same as the original author saw, particularly for darker or near-neutral colors. The CHRM chunk provides the information that allows closer color matching than that provided by gamma correction alone. Decoders can use the CHRM data to transform the image data from RGB to XYZ and thence into a perceptually linear color space such as CIE Lab. They can then partition the colors to generate an optimal palette based on the geometric distance between the two colors in CIE Lab is strongly related to how different those colors appear, unlike, for example, RGB or XYZ spaces. The resulting palette of colors, once transformed back into RGB color space, could be used for display or written into a PLTE chunk. Decoders that are part of image processing applications might also transform image data into CIE Lab space for analysis. End of page 56 of RFC-2083, PNG Portable Network Graphics, March 1997. And we are now on page 54. God, I can't even keep this. Oh, God. We're on page 57 now. In applications where color fidelity is critical, such as product design, scientific visualization, medicine, architecture, or advertising, decoders can transform the image data from source RGB to the display RGB space the monitor used to view the image. This involves calculating the matrix to go from source RGB to XYZ, the matrix to go from XYZ to display RGB, then combining them to produce the overall transformation. The decoder is responsible for implementing gamma mapping. Decoders running on platforms that have a color management system, CMS, can pass the image data, gamma, and CHRM values to the CMS for display or further processing. Decoders that provide color printing facilities can use the facilities and level 2 PostScript to specify the image data in calibrated RGB space or in device-independent color space such as XYZ. This will provide better color fidelity than a sample RGB to CMYK conversion. The PostScript language reference manual gives examples of this process. PostScript. Such decoders are responsible for implementing gamma mapping between source RGB specified in the CHRM chunk and the target printer. The PostScript interpreter is then responsible for producing the required colors. Decoders can use the CHRM data to calculate an accurate grayscale representation of a color image. Conversion from RGB to gray is simply a case of calculating the Y luminance component of XYZ, which is a weighted sum of the R, G, and V values. The weights depend on the monitor type, i.e. the values of the CHRM chunk. Decoders may wish to do this for PNG files with no CHRM chunk. In that case, a reasonable default would be the CCIR 709 primaries ITU-BT709. Do not use the original NTSC primaries unless you really do not have an image color balance for such monitor. Few monitors ever use the NTSC primaries, so such images are probably non-existent these days. 10.7 Background color. The background color given by BKGD will typically be used to fill unused screen space around the image, as well as any transparent pixels within the image. Thus, BKGD is valid and useful even when the image does not use transparency. If no BKGD chunk is present, the viewer will need to make its own decision about a suitable background color. End of page 15, on to page 58 of RFC 2083. Viewers that have a specific background against which to present the image, such as web browsers, should ignore the BKGD chunk, in effect overriding BKGD with their preferred background color or background image. The background color given by BKGD is not to be considered transparent, even if it happens to match the color given by TRNS, or, in the case of an index color image, refers to a palette index that is marked as transparent by TRNS. Otherwise, one would have to imagine something behind the background to composite against. The background color is either used as a background or ignored. It is not an intermediate layer between the PNG image and some other background. Indeed, it will be common that BKGD and TRNS specify the same color, since then a decoder that does not implement transparency processing will give the intended display, at least when no partially transparent pixels are present. 10.8 Alpha channel processing. In the most general case, the alpha channel can be used to composite a foreground image against a background image. The PNG file defines the foreground image and the transparency mask, but not the background image. Decoders are not required to support this most general case. It is expected that most will be able to support compositing against a single background color, however. The equation for computing a composited sample value is output equals alpha multiplied by foreground plus, within parentheses, 1 minus alpha multiplied by background, where alpha and the input and output sample values are expressed as fractions in the range 0 to 1. This computation should be performed with linear, non-gamma encoded sample values. For color images, the computation is done separately for R, G, and B samples. The following code illustrates the general case of compositing a foreground image over a background image. It assumes that you have the original pixel data available for the background image, and that output is to a frame buffer for display. Other variants are possible. See the comments below in the code. The code allows the sample depths and gamma values of foreground image, background image, and frame buffer /CRT all to be different. Don't assume they are the same without checking. Okay, so that's the end of page 58. We are on page 59 of RFC-2083. This code is standard C with line numbers added for reference in the comments below. Line 1 int foreground 4, so that is an array of 4 integers. And we have image pixel RGBA. Line 2 int background 3, so an array of 3 ints, background pixel RGB. Line 3 int FBPix3, so an array of 3 something or other, frame buffer pixel. Line 4 int FG underscore max sample, foreground max sample. Line 5 int BG max sample, background max sample. Line 6 int FB underscore max sample, max frame buffer sample. Line 7 int I alpha. Line 8 float alpha and comp alpha. Then on line 9 we have a few declarations that are all floats. We have float gam FG, comma lin FG, comma gam BG, comma lin BG, comma comp pix, comma GC video. Another comment, I'm not sure what line this comment belongs to because I guess the numbering is only for the actual code, not for the comments. Get max sample values in data and frame buffer. On line 10, FG max sample equals 1 bit shifted over by FG sample depth minus 1. Line 11, BG max sample equals 1 bit shifted over by BG sample depth minus 1, and 12, FB max sample equals 1 shifted over by frame buffer sample depth minus 1. Then we have a big block comment here. Get integer version of alpha. Check for opaque and transparent special cases. No compositing needed if so. We show the whole gamma decode / correct process in floating point, but it would more likely be done with lookup tables. Line 13, alpha equals foreground 3, so it is a pointer. Oh no, it's not a pointer, sorry. It's the third element in I alpha is the third element in foreground. So foreground must be, let's go back up to foreground for a second. Where is foreground? Foreground, R, G, B, and A. So foreground 3 would be the alpha. So let's go back down there. Okay, so I alpha equals foreground 3. Yep, that is sensible. I alpha, if I alpha equals 0. So that would be completely transparent, I think. And there's a comment, foreground image is transparent here. If the background image is already in the frame buffer, there is nothing to do. 15, we have an empty statement. 16, else if alpha equals FG max sample, copy foreground pixel to frame buffer. Line 17, for I equals 0, I less than 3, I plus plus, so I is from 0 to 2 inclusive, so it's going through all of the indexes of an array. Line 18, gam FG, cast to float foreground I divided by max sample. Line 19, lin FG equals power function, gam FG, with a second parameter of 1.0 divided by FG gamma. Line 20, comp pix equals lin FG. Line 21, GC video equals power function, comp pix, comma, viewing gamma divided by display gamma. Line 22, FB I equals an integer cast of GC video multiplied by FB max sample plus 0.5, and a closing bracket on line 23 for the condition I alpha equals FG max sample. End of page 59. The code is continued on page 60. There is a else statement. So this is our catch-all, it looks like. Compositing is necessary. Get floating point alpha and its complement. Note alpha is always linear. Gamma does not affect it. Line 25. Alpha equals a cast to float of I alpha divided by FG max sample. Line 26. Comp alpha equals 1.0 minus alpha. Line 27. For I equals 0. I less than 3, I plus plus. So we're going through all of the indices of an array, probably something with RGBA again. Convert foreground and background to floating point, then linearize, undo gamma encoding. 28, gam FG equals a cast to float of foreground I divided by FG max sample. Line 29, lin FG equals pow gam FG with a second parameter of 1.0 divided by FG gamma. Line 30, gam BG equals a cast to float of background I divided by BG max sample. Line 31, lin BG equals power function gam BG as the first parameter and 1.0 divided by BG gamma as the second parameter. Comment, composite. Line 32, compix equals lin FG multiplied by alpha plus lin BG times comp alpha. The comment below is gamma correct for display, convert to integer frame buffer pixel. Line 33, GC video equals power function comp pix, comma, viewing gamma divided by display gamma. 34, FB pix I equals integer cast, GC video multiplied by FB max sample plus 0.5. Closing brace on line 35 and another closing brace on line 36. Variations. If output is to another PNG image file instead of a frame buffer, lines 21, 22, 33, and 34 should be changed to be something like comment, gamma encode for storage in output file. Convert to integer sample value. Gam out equals power function compix, comma, out file gamma. Outpix I equals integer cast gamma out times max out sample plus 0.5. Also, it becomes necessary to process background sample. Sorry, let me say that again. Also, it becomes necessary to process background pixels when alpha is 0, rather than just skipping pixels. Thus, line 15 will need to be replaced by copies of lines 17 to 23, but processing background instead of foreground pixel values. That is the end of page 60. On to page 61 of RFC-2083. Bullet point. If the sample depths of the output file, foreground file, and background file are all the same, and the three gamma values also match, then the no compositing code in lines 14 to 23 reduces to nothing more than copying pixel values from the input file to the output file if alpha is 1, or copying pixel values from background to output file if alpha is 0. Since alpha is typically either 0 or 1 for the vast majority of pixels in an image, this is a great savings. No gamma computations are needed for most pixels. Bullet point. When the sample depths and gamma values all match, it may appear attractive to skip the gamma decoding and encoding lines 28 to 31, 33 to 34, and just perform line 32 using gamma encoded sample values. Although this doesn't hurt image quality too badly, the time savings are small if alpha values of 0 and 1 are special cased as recommended here. Next bullet point. If the original pixel values of the background image are no longer available, only processed frame buffer pixels left by display of the background image Then lines 30 to 31 need to extract intensity from the frame buffer pixel values using code like comment, decode frame buffer value back into linear space. GC video equals float cast fb pix I divided by fb max sample lin bg equals power function GC video comma display gamma divided by viewing gamma. However, some round-off error can result, so it is better to have the original background pixels available if at all possible. Note that lines 18 to 22 are performing exactly the same gamma computation that is done when no alpha channel is present. So if you handle the no alpha case with a lookup table, you can use the same lookup table here. Lines 28 to 31 and 33 to 34 can also be done with different lookup tables. Of course, everything here can be done in integer arithmetic. Just be careful to maintain sufficient precision all the way through. Note, in floating point, no overflow or underflow checks are needed because the input sample values are guaranteed to be between 0 and 1, and compositing always yields a result that is in between the input values inclusive. With integer arithmetic, some round-off error analysis might be needed to guarantee no overflow or underflow. End of page 61. On to page 62 of RFC-2083. When displaying a PNG image with full alpha channel, it is important to be able to composite the image against some background, even if it's only black. Ignoring the alpha channel will cause PNG images that have been converted from an associated alpha representation to look wrong. Of course, if the alpha channel is a separate transparency mask, then ignoring the alpha is a useful option. It allows the hidden parts of the image to be recovered. Even if the decoder author does not wish to implement true compositing logic, it is simple to deal with images that contain only 0 and 1 alpha values. This is implicitly true for grayscale and true color PNG files that use a TRNS chunk. For indexed color PNG files, it is easy to check whether TRNS contains any values other than 0 to 255. In this simple case, transparent pixels are replaced by the background color, while others are unchanged. If a decoder contains only this much transparency capability, it should deal with the full alpha channel by treating all non-zero alpha values as fully opaque, that is, do not replace partially transparent pixels by the background. This approach will not yield very good results for images converted from associated alpha formats, but it's better than doing nothing. 10.9 Progressive Display. When receiving images over slow transmission links, decoders can improve perceived performance by displaying interlaced images progressively. This means that as each pass is received, an approximation to the complete image is displayed based on the data received so far. One simple yet pleasing effect can be obtained by expanding each received pixel to fill a rectangle covering the yet-to-be transmitted pixel portions below and to the right of the received pixel. This process can be described by the following pseudocode. Starting row 1 through 7 equals 0, 0, 4, 0, 2, 0, 1. Starting column 1 to 7, 0, 4, 0, 2, 0, 1, 0. Row increment 1 through 7 is 8, 8, 8, 4, 4, 2, 2. Column increment 1 through 7, 8, 8, 4, 4, 2, 2, and 1. Block height 1 through 7, 8, 8, 4, 4, 2, 2, and 1. Block width 1 through 7, 8, 4, 4, 2, 2, 1, 1. Pass declared and assigned to 1, while pass is less than or equal to 7. Begin. Row declared and assigned to starting row of pass, while row is less than height on page 63. Begin. Column assigned and declared starting column pass. While the column is less than the width, begin, visit, open paren, row, comma, column, comma, min, block height pass, comma, height minus row. Then another parameter, min block width pass, comma, min minus column, and closing the function call to visit. Column colon equals, so that's an assignment and a declaration. Column colon equals column plus col underscore increment, and then within square brackets pass, so that's array access, and then an end. Row declared and assigned to row plus row increment pass, and then passes within square brackets. End, pass colon equals pass plus 1, then another end. Here the function visit, open paren, row, comma, column, comma, height, comma, width, close paren, obtains the next transmitted pixel and paints a rectangle of the specified height and width whose upper left corner is at the specified row and column using the color indicated by the pixel. Note that row and column are measured from 0, 0 at the upper left corner. If the decoder is merging the received image with a background image, it may be more convenient just to paint the received pixel positions, that is, the visit function sets only the pixel at the specified row and column, not the whole rectangle. This produces a fade-in effect as the new image gradually replaces the old. An advantage of this approach is that proper alpha or transparency processing can be done as each pixel is replaced. Painting a rectangle as described above will overwrite background image pixels that may be needed later if the pixels eventually received for those portions turn out to be wholly or partially transparent. Of course, this is only a problem if the background image is not stored anywhere off screen. 10.10 Suggested palette and histogram usage. In TrueColor PNG files, the encoder may have provided a suggested PLTE chunk for use by viewers running on index color hardware. If the image has a TRNS chunk, the viewer will need to adapt to the suggested palette for use with its desired background color. To do this, replace the palette entry closest to the TRNS color for the desired background color, or just add a palette entry for the background color. If the viewer can handle more colors, then there are PLTE entries. End of page 63, onto page 64 of RFC-2083 PNG Portable Network Graphics, March 1997. For images of color type 6, true color with alpha channel, any suggested palette should have been designed for display of the image against a uniform background of the color specified by PKGD. Viewers should probably ignore the palette if they intend to use a different background or if the BKGD chunk is missing. Viewers can use a suggested palette for display against a different background than it was intended for, but the results may not be very good. If the viewer presents a transparent true color image against a background that is more complex than a single color, it is unlikely that the suggested palette will be optimal for the composite image. In this case, it is best to perform a true color compositing step on the true color PNG image and background image. Then color quantize the resulting image. The histogram chunk is useful when a viewer cannot provide as many colors as are used in the image's palette. If the viewer is only short of food colors, it is usually adequate to drop the least used color from the palette to reduce the number of colors substantially. It's best to choose entirely new representative colors rather than trying to use a subset of the existing palette. This amounts to performing a new color quantization step. However, the existing palette and histogram can be used as the input data, thus avoiding a scan of the image data. If no palette or histogram chunk is provided, a decoder can develop its own at the cost of an extra pass over the image data. Alternatively, a default palette, probably a color cube, can be used. See also recommendations for encoders, suggested palettes, section 9.5. 10.11 Text Chunk Processing. 10.11 Text Processing. If practical, decoders should have a way to display to the user all TEXT and ZTXT chunks found in the file. Even if the decoder does not recognize a particular text keyword, the user might be able to understand it. PNG text is not supposed to contain any characters outside of the ISO 8859-1 Latin 1 character set. That is, no codes 0 to 31 or 127 to 159 except for the new line character, decimal 10, but decoders might encounter such characters anyways. Some of these characters can be safely displayed, e.g. tab, FF, and CR, decimal 9, 12, and 13 respectively. But others, especially the ESC character, decimal 27, could pose a security hazard because unexpected. End of page 64. On 65, unexpected actions may be taken by display hardware or software. To prevent such hazards, decoders should not attempt to directly display any non-Latin 1 characters except for new line and perhaps tab, FF, CR, encountered in TEXT or ZTXT chunk. Instead, ignore them or display them in a visible notation such as \NNN. See Security Considerations, section 8.5. Even though encoders are supposed to represent new lines as LF, it is recommended that decoders not rely on this. It's best to recognize all of the common new line combinations, CR, LF, and CRLF, and display each as a single new line. Tab can be expanded to the proper number of spaces needed to arrive at a column multiple of 8. Decoders running on systems with non-Latin 1 character set encoding should provide character code remapping so that Latin 1 characters are displayed correctly. Some systems may not provide all the characters defined in Latin 1. Mapping unavailable characters to a visible notation such as \NNN is a good fallback. In particular, character codes 127 to 255 should be displayed only if they are printable characters on the decoding system. Some systems may interpret such codes as control characters. For security, decoders running on such systems should not display such characters literally. Decoders should be prepared to display text chunks that contain any number of printing characters between new line characters, even though encoders are encouraged to avoid creating lines in excess of 79 characters. 11. Glossary. A to the power of B. Exponentiation. A raised to the power of B. C programmers should be careful not to misread this notation as exclusive OR. Note that in gamma-related calculations, 0 raised to any power is valid and must give a 0 result. Alpha. A value representing a pixel's degree of transparency. The more transparent a pixel, the less it hides in the background against which the image is presented. In PNG, alpha is really the degree of opacity. 0 alpha represents a completely transparent pixel, maximum alpha represents a completely opaque pixel, but most people refer to alpha as providing transparency information, not opacity information, and we continue the custom here. End of page 65, on to page 66 of RFC-2083. Ancillary chunk, a chunk that provides additional information. A decoder can still produce a meaningful image, though not necessarily the best possible image, without processing the chunk. Bit depth, the number of bits per palette index in indexed colored PNGs or per sample in other color types. This is the same value that appears in IHDR. Byte, 8 bits, also called an octet. Channel, the set of all samples of the same kind within an image. For example, all the blue samples in a true color image. The term component is also used, but not in this specification. A sample is the intersection of a channel and a pixel. Chromacity, a pair of values x, y that precisely specify the hue, though not the absolute brightness of a perceived color. Chunk, a section of a PNG file. Each chunk has a type indicated by its chunk type name. Most types of chunks also include some data. The format and meaning of the data within the chunk are determined by the type name. Composite, as a verb to form an image by merging a foreground image and a background image. Using transparency information to determine where the background should be visible, the foreground image is said to be composited against the background. CRC, cyclic redundancy check. A CRC is a type of check value designed to catch most transmission errors. A decoder calculates the CRC for the received data and compares it to the CRC that the encoder calculated, which is appended to the data. A mismatch indicates that the data was corrupted in transit. Critical chunk, a chunk that must be understood and processed by the decoder in order to produce a meaningful image from a PNG file. CRT, cathode ray tube, a common type of computer display hardware. End of page 66, on to page 67 of RFC-2083. Datastream, a sequence of bytes. This term is used rather than file to describe a byte sequence that is only a portion of a file. We also use it to emphasize that a PNG image might be generated and consumed on the fly, never appearing in a stored file at all. Deflate, the name of the compression algorithm used in standard PNG files, as well as in zip, gzip, pkzip, and other compression programs. Deflate is a member of the LZ77 family of compression methods. Filter, a transformation applied to image data in hopes of improving its compressibility. PNG uses only lossless reversible filter algorithms. Frame buffer, the final digital storage area for the image shown by a computer display. Software causes an image to appear on screen by loading it into the frame buffer. Gamma, the brightness of mid-level tones in an image. More precisely, a parameter that describes the shape of the transfer function for one or more stages in an image pipeline. The transfer function is given by the expression output equals input to the power of gamma, where both input and output are scaled to the range 0 to 1. Grayscale, an image representation in which each pixel is represented by a single sample value representing overall luminance on a scale from black to white. PNG also permits an alpha sample to be stored for each pixel of a grayscale image. Indexed color, an image representation in which each pixel is represented by a single sample that is an index into a palette or lookup table. The selected palette entry defines the actual color of the pixel. Lossless compression, any method of data compression that guarantees the original data can be reconstructed exactly bit for bit. End of page 67, on to page 68 of RFC 2083. Lossy compression, any method of data compression that reconstructs the original data approximately rather than exactly. LSB, least significant byte of a multi-byte value. Luminance, perceived brightness or grayscale level of a color. Luminance and chromacity together fully define a perceived color. LUT, lookup table. In general, a table used to transform data. In frame buffer hardware, a LUT can be used to map index color pixels into a selected set of true color values or to perform gamma correction. In software, an LUT can be used as a fast way of implementing any one-variable mathematical function. MSB, most significant byte of a multi-byte value. Palette, the set of colors available in an index color image. In PNG, a palette is an array of colors defined by red, green, and blue samples. Alpha values can also be defined for palette entries via the TRNS chunk. Pixel, the information stored for a single grid point in the image. The complete image is a rectangular array of pixels. PNG editor, A program that modifies a PNG file and preserves ancillary information, including chunks that it does not recognize. Such a program must obey the rules given in Chunk Ordering Rules, Chapter 7. Sample, a single number in the image data. For example, the red value of a pixel. A pixel is composed of one or more samples. When discussing physical data layout, in particular in image layout, section 2.3, we use sample to mean a number stored in the image array. It would be more precise but much less readable to say sample or palette index in that context. Elsewhere in the specification, sample means a color value or alpha value in the indexed color case. These are palette entries, not palette indexes. End of page 68, on to page 69 of RFC-2083 PNG Portable Network Graphics, March 1997. Sample depth, the precision in bits of color values and alpha values. In index color PNGs, the sample depth is always 8 by definition of the PLTE chunk. In other color types, it is the same as the bit depth. Scan line, 1 horizontal rows of pixels in an image. True color, an image representation in which pixel colors are defined by storing 3 samples for each pixel, representing red, green, and blue intensities, respectively. PNG also permits an alpha sample to be stored for each pixel of a true color image. White point, the chromacity of a computer's display's nominal white value. zlib, a particular format for data that has been compressed using deflate style compression. Also the name of a library implementing this method. PNG implementations need not use the zlib library, but they must conform to its format for compressed data. Section 12, or Section 12? I don't know. 12 Appendix Rationale. So I believe that is the section number. This appendix is not part of the formal PNG specification. This appendix gives the reasoning behind some of the design decisions in PNG. Many of these decisions were the subject of considerable debate. The authors freely admit that another group might have made different decisions. However, we believe that our choices are defensible and consistent. 12.1 Why a new file format? Does the world really need yet another graphics format? We believe so. GIF is no longer freely usable, but no other commonly used format can directly replace it, as is discussed in more detail below. We might have used an adaptation of an existing format, for example, GIF with an unpatented compression scheme, but this would require new code anyways. It would not be all that much easier to implement than a whole new file format. PNG is designed to be simple to implement, with the exception of the compression engine, which would be needed in any case. We feel that this is an excellent opportunity to design a new format that fixes some of the known limitations of GIF. End of page 69, on to page 70 of RFC 2083. 12.2 Why these features? The features chosen for PNG are intended to address the needs of applications that previously used the special strengths of GIF. In particular, GIF is well adapted for online communications because of its streamability and progressive display capability. PNG shares those attributes. We have also addressed some of the widely known shortcomings of GIF. In particular, PNG supports true color images. We know of no widely used image format that losslessly compresses true color images as effectively as PNG does. We hope that PNG will make use of true color images more practical and widespread. Some form of transparency control is described for applications in which images are displayed against a background or together with other images. GIF provided a simple transparent color specification for this purpose. PNG supports a full alpha channel as well as transparent color specifications. This allows both highly flexible transparency and compression efficiency. Robustness against transmission errors has been an important consideration. For example, images transferred across internet are often mistakenly processed as text, leading to file corruption. PNG is designed so that such errors can be detected quickly and reliably. PNG has been expressly designed not to be completely dependent on a single compression technique. Although deflate/inflate compression is mentioned in this document, PNG would still exist without it. 12.3. Why not these features? Some features have been deliberately omitted from PNG. These choices were made to simplify implementation of PNG, promote portability and interchangeability, and make the format as simple and foolproof as possible for users. In particular, end of page 70 on to 71 of RFC-2083. There is no uncompressed variant of PNG. It is possible to store uncompressed data by using only uncompressed deflate blocks, a feature normally used to guarantee that deflate does not make incompressible data much larger. However, PNG software must support full deflate/inflate. Any software that is not compliant with the PNG standard. The two most important features of PNG, portability and compression, are absolute requirements for online applications, and users demand them. Failure to support full deflate/inflate compromises both of these objectives. There is no lossy compression in PNG. Existing formats, such as JFIF, already handle lossy compression well. Furthermore, available lossy compression methods, e.g. JPEG, are far from foolproof. A poor choice of quality level can ruin an image. To avoid user confusion and unintentional loss of information, we feel it is best to keep lossy and lossless formats strictly separate. Also, lossy compression is complex to implement. Adding JPEG support to a PNG decoder might increase its size by an order of magnitude. This would certainly cause some decoders to omit support for the feature, which would destroy our goal of interchangeability. There is no support for CMYK or other unusual color spaces. Again, this is in the name of promoting portability. CMYK, in particular, is far too device dependent to be useful as a portable image representation. There is no standard chunk for thumbnail views of images. In discussions with software vendors who use thumbnails in their products, it has become clear that most would not use a standard thumbnail chunk. For one thing, every vendor has a different idea of what the dimensions and characteristics of a thumbnail ought to be. Also, some vendors queue thumbnails in separate files to accommodate varied image formats. They are not going to stop doing that simply because of a thumbnail chunk in one new format. Proprietary chunks containing vendor-specific thumbnails appear to be more practical than a common thumbnail format. It is worth noting that private extensions to PNG could easily add these features. We will not, however, include them as part of the basic PNG standard. End of page 71, on to page 72 of RFC 2083. PNG also does not support multiple images in one file. This restriction is a reflection of the reality that many applications do not need and will not support multiple images per file. In any case, single images are a fundamentally different sort of object from sequences of images. Rather than make false promises of interchangeability, we have drawn a clear distinction between single image and multi-image formats. PNG is a single image format, but see multiple image extensions, section 8.4. 12.4. Why not use Format X? Numerous existing formats were considered before deciding to develop PNG. None could meet the requirements we felt were important for PNG. GIF is no longer suitable as a universal standard because of legal entanglements. Although just replacing GIF's compression method would avoid that problem, GIF does not support true color images, alpha channels, or gamma correction. The spec has more subtle problems, too. Only a small subset of the GIF 89 spec is actually portable across a variety of implementations, but there is no codification of the most portable part of the spec. TIFF is far too complex to meet our goals of simplicity and interchangeability. Defining a TIFF subset would meet that objection, but would frustrate users, making the reasonable assumption that a file saved as TIFF from their existing software would load into a program supporting our flavor of TIFF. Furthermore, TIFF is not designed for stream processing, has no provisions for progressive display, and does not currently provide any good, legally unencumbered, lossless compression method. IFF also has been suggested, but is not suitable in detail. Available image representations are too machine-specific or not adequately compressed. The overall chunk structure of IFF is a useful concept that PNG has liberally borrowed from, but we did not attempt to be bit-for-bit compatible with IFF chunk structure. Again, this is due to detailed issues, notably the fact that IFF forms are not designed to be Let me try this again. Again, this is due to detailed issues, notably the fact that IFF forms are not designed to be serially writable. Lossless JPEG is not suitable because it does not provide for the storage of index color images. Furthermore, its lossless true color compression is often inferior to that of PNG. End of page 72, on to page 73 of RFC-2083. 12.5 byte order. It has been asked why PNG uses network byte order. We have selected one byte ordering and used it consistently. Which order in particular is of little relevance, but network byte order has the advantage that routines to convert to and from it are already available on any platform that supports TCP/IP networking, including all PC platforms. The functions are trivial and will be included in the reference implementation. Alright, quick little aside. I was looking at endianness, and it looks like network byte order is big endian order, and at 8 minutes and 30 seconds of this computer file video on endianness, he talks about how the internet has decided to use big endianness. Also found an RFC on network byte order, which also looks like, if you wanted to get more familiar with that. But anyways, back to reading. 12.6 interlacing. 12.6 interlacing. PNG's two-dimensional interlacing scheme is more complex to implement than GIF's line-wise interlacing. It also costs a little more in file size, however it yields an initial image 8 times faster than GIF. The first pass transmits only 1/64th of the pixels compared to 1/8 for GIF. Although this initial image is coarse, it is useful in many situations. For example, if the image is a World Wide Web image map that the user has seen before, PNG's first pass is often enough to determine where to click. The PNG scheme also looks better than GIF's because horizontal and vertical resolution never differ by more than a factor of 2. This avoids the odd stretched look seen when interlaced GIFs are filled in by replicating scan lines. Preliminary results show that small text in an interlaced PNG... Well, let me scroll down here. Preliminary results show that small text in an interlaced PNG image is typically readable about twice as fast as in an equivalent GIF, i.e. after PNG's 5th pass, or 25% of the image data, instead of GIF's 3rd pass, or 50%. This is again due to PNG's more balanced increase in resolution. 12.7. Why gamma? It might seem natural to standardize on storing sample values that are linearly proportional to light intensity, that is, have gamma of 1.0, but in fact it is common for images to have a gamma of less than 1. There are 3 good reasons for this. Bullet point 1. For reasons detailed in Gamma Tutorial, Chapter 13, all video cameras apply a gamma correction function to the intensity information. This causes the video signal to have a gamma of about 0.5 relative to the light intensity in the original scene. Thus, images obtained by frame-grabbing video already have a gamma of about 0.5. Bullet point number 2, the human eye has a non-linear response to intensity, so linear encoding of samples either wastes sample codes in the bright areas of the image or provides too few sample codes to avoid banding artifacts in dark areas of the image, or both. At least 12 bits per sample are needed to avoid, page 74, to avoid visible artifacts in linear encoding with a 100 to 1 image intensity range. An image gamma in the range 0.3 to 0.5 allocates sample values in a way roughly corresponds to the eye's response, so that 8 bits per sample are enough to avoid artifacts caused by insufficient sample precision in almost all images. This makes gamma encoding a much better way of storing digital images than the simpler linear encoding. Third and final bullet point, many images are created on PCs or workstations with no gamma correction hardware and no software willing to provide gamma correction either. In these cases, the images have had their lighting and color chosen to look best on this platform. They can be thought of as having manual gamma correction built in. To see what the image author intended, it is necessary to treat such images as having a file_gamma value in the range of 0.4 to 0.6, depending on the room lighting level that the author was working in. In practice, image gamma values around 1.0 and around 0.5 are both widely found. Older image standards such as GIF often do not account for this fact. The JFIF standard specifies that images in that format should use linear samples, but many JFIF images found on the internet actually have a gamma of somewhere around 0.4 to 0.5. The variety of images found and the variety of systems that people display them on have led to widespread problems with images appearing too dark or too light. PNG expects viewers to compensate for image gamma at the time that the image is displayed. Another possible approach is to expect encoders to convert all images to a uniform gamma at encoding time. While that method would speed viewers slightly, it has fundamental flaws. Bullet point, gamma correction is inherently lossy due to quantization and round-off error, requiring conversion at encoding time, thus causes irreversible loss. Since PNG is intended to be a lossless storage format, this is undesirable. We should store unmodified source data. The encoder might not know the source gamma value. If the decoder does gamma correction at viewing time, it can adjust the gamma, change the display brightness in response to feedback from a human user. The encoder has no such recourse. Whatever standard gamma we settled on would be wrong for some displays, hence viewers would still need gamma correction capability. End of page 74, on to page 75. Since there will always be images with no gamma or an incorrect recorded gamma, good viewers will need to incorporate gamma adjustment code anyways. Gamma correction at viewing time is thus the right way to go. See Gamma Tutorial Chapter 13 for more information. 12.8 Non-Premultiplied Alpha. PNG uses unassociated or non-premultiplied alpha so that images with separate transparency masks can be stored losslessly. Another common technique, premultiplied alpha, stores pixel values premultiplied by the alpha fraction. In effect, the image is already composited against a black background. Any image data hidden by the transparency mask is irretrievably lost by that method, since multiplying by a 0 alpha value always produces 0. Some image rendering techniques generate images with premultiplied alpha. The alpha value actually represents how much of a pixel is covered by the image. This representation can be converted to PNG by dividing the sample values by alpha except where alpha is 0. The result will look good if displayed by a viewer that handles alpha properly, but will not look very good if the viewer ignores the alpha channel. Although each form of alpha storage has its disadvantages, Although each form of alpha storage has its advantages, we did not want to require all PNG viewers to handle both forms. We standardized on non-premultiplied alpha as being the lossless and more general case. 12.9 Filtering. PNG includes filtering capability because filtering can significantly reduce the compressed size of true color and grayscale images. Filtering is also sometimes of value on index color images, although this is less common. The filter algorithms are defined to operate on bytes rather than pixels. This gains simplicity and speed with very little cost and compression performance. Tests have shown that filtering is usually ineffective for images with fewer than 8 bits per sample, so providing pixel-wise filtering for such images would be pointless. For 16-bit/sample data, byte-wise filtering is nearly as effective as pixel-wise filtering because MSBs are predicted from adjacent MSBs and LSBs are predicted from adjacent LSBs. Alright, page 76 of RFC-2083. The encoder is allowed to change filters for each new scanline. This creates no additional complexity for decoders, since a decoder is required to contain defiltering logic for every filter type anyways. The only cost is an extra byte per scanline in the pre-compression data stream. Our test showed that when the same filter is selected for all scanlines, this extra byte compresses away to almost nothing, so there is little storage costs compared to a fixed filter specified for the whole image, and the potential benefits of adapting filtering are too great to ignore. Even with the simplistic filter choice heuristics so far discovered, adaptive filtering usually outperforms fixed filters. In particular, an adaptive filter can change behavior for successive passes of an interlaced image. A fixed filter cannot. 12.10 Text strings. Most graphics file formats include the ability to store some textual information along with the image, but many applications need more than that. They want to be able to store several identifiable pieces of text. For example, a database using PNG files to store medical x-rays would likely want to include patient's name, doctor's name, etc. A simple way to do this in PNG would be to invent new private chunks holding text. The disadvantage of such an approach is that other applications would have no idea what was in those chunks and would simply ignore them. Instead, we recommend that textual information be stored in standard TXT chunks with suitable keywords. Use of TXT tells any PNG viewer that the chunk contains text that might be of interest to a human user. Thus, a person looking at the file with another viewer will still be able to see the text and even understand what it is if the keywords are reasonably self-explanatory. To this end, we recommend spelled-out keywords, not abbreviations that will be hard for a person to understand. Saving a few bytes on a keyword is false economy. The ISO 8859-1 Latin 1 character set was chosen as a compromise between functionality and portability. Some platforms cannot display anything more than 7-bit ASCII characters, while others can handle characters beyond the Latin 1 set. We felt that Latin 1 represents a widely useful and reasonably portable character set. Latin 1 is a direct subset of character sets commonly used on popular platforms such as Microsoft Windows and X Windows. It can also be handled on Macintosh systems with a simple remapping of characters. There is presently no provision for text employing character sets other than Latin 1. We recognize that the need for other character sets will increase. However, PNG already requires that, page 77, that programmers implement a number of new and unfamiliar features, and text representation is not PNG's primary purpose. Since PNG provides for the creation and public registration of new ancillary chunks of general interest, we expect that text chunks for other characters such as Unicode eventually will be registered and increase gradually in popularity. 12.11 PNG file signature. The first 8 bytes of a PNG file always contain the following values: In decimal, 137, 80, 78, 71, 13, 10, 26, and 10. Hexadecimal, 89, 50, 4E, 47, 0D, 0A, 1A, 0A. ASCII C notation, \211, PNG, \R, \N, \032, \N. This signature both identifies the file as a PNG file and provides for immediate detection of common file transfer problems. The first 2 bytes distinguish PNG files on systems that expect the first 2 bytes to identify the file type uniquely. The first byte is chosen as a non-ASCII value to reduce the probability that a text file may be misrecognized as a PNG file. Also, it catches bad file transfers that clear bit 7. Bytes 2 through 4 name the format. The CR-LF sequence catches bad file transfers that alter new line sequences. The Control Z character stops file display under MS-DOS. The final line feed checks for the inverse of the CR-LF translation problem. A decoder may further verify the next 8 bytes contain an IHDR chunk header with the correct chunk length. This will catch bad transfers that drop or alter null 0 bytes. Note that there is no version number in the signature, nor indeed anywhere in the file. This is intentional. The chunk mechanism provides a better, more flexible way to handle format extensions, as explained in chunk naming conventions 12.13. 12.12 Chunk Layout. The chunk design allows decoders to skip unrecognized or uninteresting chunks. It is simply necessary to skip the appropriate number of bytes as determined from the length field. Limiting chunk length to 2 to the power of 31 minus 1 bytes avoids possible problems for implementations that cannot conveniently handle 4-byte unsigned values. In practice, chunks will usually be much shorter than that anyways. End of page 77, on to page 78. A separate CRC is provided for each chunk in order to detect badly transferred images as quickly as possible. In particular, critical data such as the image dimensions can be validated before being used. The chunk length is excluded from the CRC so that the CRC can be calculated as the data is generated. This avoids a second pass over the data in cases where the chunk length is not known in advance. Excluding the length from the CRC does not create any extra risk of failing to discover file corruption, since if the length is wrong, the CRC check will fail. The CRC will be computed on the wrong set of bytes and then be tested against the wrong value from the file. 12.13 Chunk Naming Convention. The chunk naming conventions allow safe, flexible extension of the PNG format. This mechanism is much better than a format version number because it works on a feature-by-feature basis rather than being an overall indicator. Decoders can process newer files if and only if the files use no unknown critical features, as indicated by finding unknown critical chunks. Unknown ancillary chunks can be safely ignored. We decided against having an overall format version number because experience has shown that format version numbers hurt portability as much as they help. Version numbers tend to be set unnecessarily high, leading to older decoders rejecting files that they could have processed. This was a serious problem for several years after the GIF89 spec came out, for example. Furthermore, private extensions can be made either critical or ancillary, and standard decoders should react appropriately. Overall, version numbers are no help for private extensions. A hypothetical chunk for vector graphics would be a critical chunk, since if ignored, important parts of the intended image would be missing. A chunk carrying the Mandelbrot set coordinates for a fractal image would be ancillary, since other applications could display the image without understanding what the image represents. In general, a chunk type should be made critical only if it is impossible to display a reasonable representation of the image without interpreting that chunk. End of page 78, on to page 79. The public-private property bit ensures that any newly defined public chunk type cannot conflict with proprietary chunks that could be in use somewhere. However, this does not protect users of private chunk names from the possibility that someone else may use the same chunk name for a different purpose. It is a good idea to put additional identifying information at the start of the data for any private chunk type. When a PNG file is modified, certain ancillary chunks may need to be changed to reflect changes in other chunks. For example, a histogram chunk needs to be changed if the image data changes. If the file editor does not recognize histogram chunks, copying them blindly to a new output file is incorrect. Such chunks should be dropped. The safe/unsafe property bit allows ancillary chunks to be marked appropriately. Not all possible modification scenarios are covered by the safe/unsafe semantics. In particular, chunks that are dependent on the total file contents are not supported. An example of such a chunk is an index of IDAT chunk locations within the file. Adding a comment chunk would inadvertently break the index. Definitions of such chunks is discouraged. If absolutely necessary for a particular application, such chunks can be made critical chunks with consequent loss of portability to other applications. In general, ancillary chunks can depend on critical chunks but not on other ancillary chunks. It is expected that mutually dependent information should be put into a single chunk. In some situations, it may be unavoidable to make one ancillary chunk dependent on another. Although the chunk property bits are insufficient to represent this case, a simple solution is available. In the dependent chunk, record the CRC of the chunk depended on. It can then be determined whether that chunk has been changed by some other program. The same technique can be useful for other purposes. For example, if a program relies on the palette being in a particular order, it can store a private chunk containing the CRC of the PLTE chunk. If this value matches when the file is again read in, then it provides high confidence that the palette has not been tampered with. Note that it is not necessary to mark the private chunk unsafe to copy when this technique is used. Thus, a private chunk can survive other editing of the file. End of page 79, on to page 80. RFC-2083. 12.14 Palette histograms. Palette histograms, section 12.14. A viewer may not be able to provide as many colors as are listed in the image's palette. For example, some colors could be reserved by a window system. To produce the best results in this situation, it is helpful to have information about the frequency with which each palette index actually appears in order to choose the best palette for dithering or to drop the least used colors. Since images are often created once and viewed many times, it makes sense to calculate this information in the encoder, although it is not mandatory for the encoder to provide it. Other image formats have usually addressed this problem by specifying that the palette entries should appear in order of frequency of use. That is an inferior solution because it doesn't give the viewer nearly as much information. The viewer can't determine how much damage will be done by dropping the last few colors, nor does a sorted palette give enough information to choose a target palette for dithering, in the case that the viewer needs to reduce the number of colors substantially. A palette histogram provides the information needed to choose such a target palette without making a pass over the image data. End of page 80, on to page 81 of RFC 2083. Appendix Gamma Tutorial. This appendix is not part of the formal PNG specification. It would be convenient for graphics programmers if all of the components of an imaging system were linear. The voltage coming from an electronic camera would be directly proportional to the intensity, power of light in the scene. The light emitted by a CRT would be directly proportional to its input voltage, and so on. However, real-world devices do not behave that way. All CRT displays, almost all photographic film, and many electronic cameras have nonlinear signal-to-light intensity or intensity-to-signal characteristics. Fortunately, all of these nonlinear devices have a transfer function that is approximated fairly well by a single type of mathematical function, a power function. This power function has the general equation output equals input to the power of gamma, where hat symbol, the caret symbol, denotes exponentation, and gamma, often printed using the Greek letter gamma, thus its name, is simply the exponent of the power function. By convention, input and output are both scaled to the range 0 to 1, with 0 representing black and 1 representing maximum white or red, etc. Normalized in this way, the power function is completely described by a single number, the exponent gamma. So, given a particular device, we can measure its output as a function of its input, fit a power function to this measured transfer function, extract the exponent, and call it gamma. We often say this device has a gamma of 2.5 as shorthand for this device has a power law response with an exponent of 2.5. We can also talk about gamma of a mathematical transform or of a lookup table in a frame buffer, so long as the input and output of the thing are related by the power law expression above. How do gammas combine? Real imaging systems will have several components, and more than one of these can be nonlinear. If all of the components have transfer characteristics that are power functions, then the transfer function of the entire system is also a power function. The exponent gamma of the whole system's transfer function is just the product of all of the individual exponents, gammas, of the separate stages in the system. End of page 81, on to page 82 of RFC-2083. Also, stages that are linear pose no problem, since a power function with an exponent of 1.0 is really a linear function. So, a linear transfer function is just a special case of a power function with a gamma of 1.0. Thus, as long as our imaging system contains only stages with linear and power law transfer functions, we can meaningfully talk about the gamma of the entire system. This is indeed the case with most real imaging systems. What should overall gamma be? If the overall gamma of an imaging system is 1.0, its output is linearly proportional to its input. This means that the ratio between the intensities of any two areas in the reproduced image will be the same as it was in the original scene. It might seem that this should always be the goal of an imaging system, to accurately reproduce the tones of the original scene. Alas, that is not the case. When the reproduced image is to be viewed in bright surround conditions, where other white objects nearby in the room have about the same brightness as white in the image, an overall gamma of 1.0 does indeed give a real-looking reproduction of a natural scene. Photographic prints viewed under room light and computer displays in bright rooms, Photographic prints viewed under room light and computer displays in bright room light are typically bright surround viewing conditions. However, sometimes images are intended to be viewed in dark surround conditions, where the room is substantially black except for the image. This is typical of the way movies and slides transparencies are viewed by projection. Under these circumstances, an accurate reproduction of the original scene results in an image that human viewers judge as flat and lacking in contrast. It turns out that the projected image needs to have a gamma of about 1.5 relative to the original scene for viewers to judge it natural. Thus, slide film is designed to have a gamma of about 1.5, not 1.0. There is also an intermediate condition called dim surround, where the rest of the room is still visible to the viewer, but is noticeably darker than the reproduced image itself. This is typical of television viewing, at least in the evening, as well as subdued light computer work areas. In dim surround conditions, the reproduced image needs to have a gamma of about 1.25 relative to the original scene in order to look natural. End of page 82, on to page 83 of RFC-2083. The requirement for boosted contrast, gamma, in dark surround conditions is due to the way the human visual system works and applies equally well to computer monitors. Thus, a PNG viewer trying to achieve the maximum realism for the image it displays really needs to know what the room lighting conditions are and adjust the gamma of the display image accordingly. If asking the user about room lighting conditions is inappropriate or too difficult, just assume that the overall gamma, viewing gamma, as defined below, should be 1.0 or 1.25. That's all that most systems that implement gamma correction should do. What is a CRT's gamma? All CRT's displays have a power law transfer characteristic with a gamma of about 2.5. This is due to the physical process involved in controlling the electron beam in the electron gun and has nothing to do with the phosphor. An exception to this rule is fancy calibrated CRTs that have internal electronics to alter their transfer function. If you have one of these, you probably should believe what the manufacturer tells you its gamma is. But in all other cases, assuming 2.5 is likely to be pretty accurate. There are various images around that purport to measure gamma, usually by comparing the intensity of an area containing alternating white and black with a series of areas of continuous gray of different intensities. These are usually not reliable. Test images that use a checkerboard pattern of black and white are the worst, because a single white pixel will be reproduced considerably darker than a large area of white. And an image that uses alternating black and white horizontal lines, such as the gamma.png test image at ftp://ftp://ftp.uu.net/graphics/png/images/suite/gamma.png is much better, but even it may be inaccurate at high picture settings on some CRTs. If you have a good photometer, you can measure the actual light output of a CRT as a function of input voltage and fit a power function to the measurements. However, note that this procedure is very sensitive to the CRT's black level adjustment, somewhat sensitive to its picture adjustment, and also affected by ambient light. Furthermore, CRTs spread some light from bright areas of an image onto nearby darker areas. A single bright spot against a black background may be seen to have a halo. Your measuring technique will need to minimize the effects of this. End of page 83. On to page 84 of RFC 2083. Because of the difficulty of measuring gamma using either test images or measuring equipment, you are usually better off just assuming gamma is 2.5 rather than trying to measure it. What is gamma correction? A CRT has a gamma of 2.5, and we can't change that. To get an overall gamma of 1.0 or somewhere near that for an imaging system, we need to have at least one other component of the image pipeline that is nonlinear. If, in fact, there is only one nonlinear stage in addition to the CRT, then it's traditional to say that the CRT has a certain gamma and that the other nonlinear stage provides gamma correction to compensate for the CRT. However, exactly where the correction is done depends on the circumstance. In all broadcast video systems, gamma correction is done in the camera. This choice was made in the days when television electronics were all analog, and a good gamma correction circuit was expensive to build. The original NTSC video standard required gammas to have a transfer function with a gamma of 1 to 2.2, or is that 1 divided by 2.2? Maybe that's 1 divided by 2.2, I don't know. Or about 0.45. Recently, a more complex two-part transfer function has been adopted. There's a link here, SMPTE-170M. I believe that's an internal file link. But its behavior can be well approximated by a power function with a gamma of 0.5. When the resulting image is displayed on a CRT with a gamma of 2.5, the image on screen ends up with a gamma of about 1.25 relative to the original scene, which is appropriate for dim surround viewing. These days, video signals are often digitized and stored in computer frame buffers. This works fine, but remember that gamma correction is built into the video signal, and so the digitized video has a gamma of about 0.5 relative to the original scene. Computer rendering programs often produce linear samples. To display these correctly, intensity on the CRT needs to be directly proportional to the sample values in the frame buffer. This can be done with a special hardware lookup table between the frame buffer and the CRT hardware. The lookup table, often called LUT, is loaded with a mapping that implements a power function with a gamma of 0.4, thus providing gamma correction for the CRT gamma. Thus, gamma correction sometimes happens before the frame buffer, sometimes after. As long as images created in a particular environment are always displayed in that environment, everything is fine. But when people try to exchange images, differences in gamma correction conventions often result in images that seem far too bright and washed out, or far too dark and contrasty. End of page 84, on to page 85 of RFC-2083. Let's make sure I can understand the ideas here. Okay, yeah. Gamma encoded samples are good. So, is it better to do gamma correction before or after the frame buffer? In an ideal world, sample values would be stored in floating point. There would be lots of precision, and it wouldn't really matter much. But in reality, we're always trying to store images in as few bits as we can. If we decide to use samples that are linearly proportional to intensity and do the gamma correction in the frame buffer LUT, it turns out that we need to use at least 12 bits for each of red, green, and blue to have enough precision and intensity. With any less than that, we will sometimes see contour bands or mock bands in the darker areas of the image where two adjacent sample values are still far enough apart in intensity for the difference to be visible. However, through an interesting coincidence, the human eye's subjective perception of brightness is related to the physical simulation of light intensity in a manner that is very much like the power function used for gamma correction. If we apply gamma correction to measured or calculated light intensity before quantizing to an integer for storage in a frame buffer, we can get away with using many fewer bits to store the image. In fact, 8 bits per color is almost always sufficient to avoid contouring artifacts. This is because, since gamma correction is so closely related to human perception, we are assigning our 256 available sample codes to intensity values in a manner that approximates how visible those intensity values are to the eye. Compared to linear sample image, we allocate fewer sample values to brighter parts of the tonal range and more sample values to the darker portions of the tonal range. Thus, for the same apparent image quality, images using gamma-encoded sample values need only about 2/3 as many bits of storage as images using linear samples. Out of page 85, on to page 86 of RFC 2083. General gamma handling. When more than two nonlinear transfer functions are involved in the image pipeline, the term gamma correction becomes too vague. If we consider a pipeline that involves capturing or calculating an image, storing it in an image file, reading the file, and displaying the image on some sort of display screen, there are at least 5 places in the pipeline that could have nonlinear transfer functions. Let's give each a specific name for their characteristic gamma. Camera gamma, the characteristics of the image sensor. Encoded gamma, the gamma of any transformation performed by the software writing the image file. Decoding gamma, the gamma of any transformation performed by the software reading the image file. LUT gamma, the gamma of the frame buffer LUT if present. CRT gamma, the gamma of the CRT, generally 2.5. In addition, let's add a few other names. File gamma, the gamma of the image in the file relative to the original scene. This is file gamma equals camera gamma multiplied by encoding gamma. Let's say that again because I kind of stuttered over that. File gamma is equal to camera gamma multiplied by encoding gamma. Display gamma, the gamma of the display system downstream of the frame buffer. This is display gamma equals LUT gamma multiplied by CRT gamma. Viewing gamma, the overall gamma that we want to obtain to produce pleasing images. Dash, 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 generally 1.0 to 1.5. End of page 86, onto page 87 of RFC 2083. The file gamma value, as defined above, is what goes in the gamma chunk in a PNG file. The file gamma is not 1.0. We know that gamma correction has been done on the sample values in the file, and we could call them gamma corrected samples. However, since there can be so many different values of the gamma in the image display chain, and some of them are not known at the time the image is written, the samples are not really being corrected for a specific display condition. We are really using a power function in the process of encoding an intensity range into a small integer field. And so it is more correct to say gamma encoded samples instead of gamma corrected samples. When displaying an image file, the image decoded program is responsible for making the overall gamma of the system equal to the desired viewing gamma by selecting the decoded gamma appropriately. When displaying a PNG file, the gamma chunk provides the file gamma value. The display gamma may be known for this machine, or it might be obtained from a system software, or the user might have to be asked what it is. The correct viewing gamma depends on lighting conditions and what will generally have to come from the user. Ultimately, you should have file gamma multiplied by decoding gamma multiplied by display gamma equals viewing gamma. Some specific examples. In digital video systems, camera gamma is about 0.5 by declaration of the various video standards documents. CRT gamma is 2.5 as usual, while encoding gamma, decoding gamma, and LUT gamma are all 1.0. As a result, viewing gamma ends up being about 1.25. On frame buffers that have hardware gamma correction tables and that are calibrated to display linear samples correctly, display gamma is 1.0. Many workstations and X terminals and PC displays lack gamma correction lookup tables. Here, LUT gamma is always 1.0, so display gamma is 2.5. End of page 87, on to 88 of RFC 2083. On the Macintosh, there is a LUT. By default, it is loaded with a table whose gamma is about 0.72, giving a display gamma, LUT, and CRT combined of about 1.8. Some Macs have a gamma control panel that allows gamma to be changed to 1.0, 1.2, 1.4, 1.8, or 2.2. These settings load alternate LUTs that are designed to give a display gamma that is equal to the label on the selected button. Thus, the gamma control panel setting can be used directly as display gamma in decoder calculations. On recent ASCII systems, there is a hardware gamma correction table whose contents are controlled by the privileged gamma program. The gamma of the table is actually the reciprocal of the number that gamma prints, and it does not include the CRT gamma. To obtain the display gamma, you need to find the ASCII system gamma either by looking in a file or asking the user, and then calculating display gamma equals 2.5 divided by ASCII system gamma. You will find SGI systems with the system gamma set to 1.0 and 2.2 or higher, but the default when machines are shipped is 1.7. A note about video gamma: the original NTSC video standards specified a simple power law camera transfer function with a gamma of 1 divided by 2.2 or 0.45. This is not possible to implement exactly in analog hardware because the function has infinite slope at x equals 0, so all cameras deviated to some degree from this ideal. More recently, a new camera transfer function that is physically resizable has been accepted as a standard SMPTE-170M. It is V out equals 4.5 multiplied by V in if V in is less than 0.018. V out equals 1.099 multiplied by, within parentheses, V in to the power of 0.45 minus 0.099 if V in is greater than or equal to 0.018. Where V in and V out are measured on a scale of 0 to 1, although the exponent remains 0.45, the multiplication and subtraction change the shape of the transfer function, so it is no longer a pure power function. If you want to perform extremely precise calculations on video signals, you should use the expression above or its inverse as required. However, PNG does not provide a way to specify that an image uses this exact transfer function. The gamma chunk always assumes a pure power law function. If we plot the two-part transfer function above along with the family of pure power functions, we find that a power function with a gamma of about 0.5 to 0.52, not 0.45, most closely approximates the transfer function. Thus, when writing a end of page 88 onto page 89, thus, when writing a PNG file with data obtained from digitizing the output of a modern video camera, the gamma chunk should contain 0.5 or 0.52, not 0.45. The remaining difference between the true transfer function and the power function is significant for almost all purpose. In fact, the alignment errors in most cameras are likely to be larger than the difference between these functions. The designers of PNG deemed the simplicity and flexibility of a power law definition of gamma to be more important than being able to describe the SMPTE-170M transfer curve exactly. The PAL and ASCII video standards specify a power law camera transfer function with a gamma of 1 divided by 2.8 or 0.36 - not the 1 divided by 2.2 of NTSC. However, this is too low in practice, so real cameras are likely to have their gamma set close to NTSC in practice. Just guessing 0.45 or 0.5 is likely to give you viewable results, but if you want precise values, you'll probably have to measure the particular camera. Further reading: if you have access to the World Wide Web, read Charles Poynton's CharlesPoynton excellent Gamma FAQ, and there's a link, Gamma FAQ. If we hover over this, maybe it'll show us. https://tools.ietf.org/html/RFC-2083 #ref Gamma FAQ. Okay, so that doesn't really give me any information, sorry. Okay, so 14 appendix color tutorial. This appendix is not part of the formal PNG specification about chromacity. The CHRM chunk is used together with the gamma chunk to convey precise color information so that PNG image can be displayed or printed with better color fidelity than is possible without this information. The preceding chapters state how this information is encoded in a PNG image. This tutorial briefly outlines the underlying color theory for those who might not be familiar with it. Note that displaying an image with incorrect gamma will produce much larger color errors than failing to use the chromacity data. First, be sure to monitor setup and gamma correction right, then worry about chromacity. The problem. The color of an object depends not only on the precise spectrum of light emitted or reflected from it, but also on the observer, their species, and what else they can see at the time. Even what, end of page 89 onto page 90. So, what else they can see at the time, what else they can see at the same time, even what they have recently looked at. Furthermore, two very different spectra can produce exactly the same color sensation. Color is not an objective property of real-world objects, it is a subjective biological sensation. However, by making some simplifying assumptions, such as we are talking about human vision, it is possible to produce a mathematical model of color and thereby obtain good color accuracy. Device-dependent color. Display the same RGB data on 3 different monitors side by side. You will get a noticeably different color balance on each display. This is because each monitor emits a slightly different shade and intensity of red, green, and blue light. RGB is an example of a device-dependent color model. The color you get depends on the device. This also means that a particular color, represented as, say, RGB 87, 146, 116 on a monitor, might have to be specified as RGB 98, 123, 104 on another to produce the same color. Device-independent color. A full physical description of a color would require specifying the exact spectral power distribution of the light source. Fortunately, the human eye and brain are not so sensitive as to require exact reproduction of a spectrum. Mathematical device-independent color models exist that describe fairly well how a particular color will be seen by humans. The most important device-independent color model, to which all others can be related, was developed by the International Lighting Committee, CIE in French, and is called XYZ. In XYZ, X is the sum of a weighted power distribution over the whole visible spectrum, so are Y and Z, each with different weights. Thus, any arbitrary spectral power distribution is condensed down to just 3 floating point numbers. The weights were derived from color matching experiments done on human subjects in the 1920s. CIE XYZ has been an international standard since 1931, and it has a number of useful properties. Bullet point. 2 colors with the same XYZ values will look the same to humans. 2 colors with different XYZ values will not look the same. The Y value represents all the brightness information, luminance. The XYZ color of any object can be objectively measured. End of page 90, on to page 91. The XYZ color of any object can be objectively measured. Color models based on XYZ have been used for many years by people who need accurate control of color, lighting engineers for film and TV, paint and dyestuffs manufacturers, and so on. They are thus proven in industrial use. Accurate device-independent color started to spread from high-end specialized areas into the mainstream during the late 1980s and early 1990s, and PNG takes notice of that. Calibrated device-dependent color. Traditionally, image file formats have used uncalibrated device-dependent color. If the precise details of the original display device are known, it becomes possible to convert the device-dependent colors of a particular image to device-independent ones, making simplifying assumptions such as working with CRTs, which are much easier than printers. All we need to know are the XYZ values of each primary color and the CRT underscore gamma. So why does PNG not store images in XYZ instead of RGB? Well, 2 reasons. First, storing images in XYZ would require more bits of precision, which would make the files bigger. Second, all programs would have to convert the image data before viewing it, whether calibrated or not. All variants of RGB are close enough that undemanding viewers can get by with simply displaying the data without color correction by storing calibrated RGB. PNG retains compatibility with existing programs that expect RGB data, yet provides enough information for conversion to XYZ in applications that need precise color. Thus, we get the best of both worlds. What are chromacity and luminance? Chromacity is an objective measurement of the color of an object. Leaving aside the brightness information, chromacity uses two parameters, x and y, which are readily calculated from XYZ. So lowercase x equals capital X divided by, and then within parentheses, x plus y plus z, and those are all capitals. Lowercase y equals uppercase y divided by, all capitals, x plus y plus z. Another way to say this would be lowercase x equals capital X all over x plus y plus z, and y equals uppercase y all over x plus y plus z. XYZ colors having the same chromacity values will appear to have the same hue, but they can vary in absolute brightness. Notice that XY are dimensionless ratios, so they have the same values no matter what units we've used for XYZ. End of page 91 of RFC-2083, on to page 92. The Y value of an XYZ color is directly proportional to its absolute brightness and is called the luminance of the color. We can describe a color either by XYZ coordinates or by chromacity, x, y plus luminance y. The XYZ form has the advantage that it is linearly related to, and then within parentheses, linear, gamma equals 1.0 RGB color spaces. How are computer monitors described? The white point of a monitor is the chromacity x, y of the monitor's nominal white, that is the color produced when R, G, B equals maximum. So when R, G, and B are all the maximum value, I assume from reading that. It's customary to specify monitor colors by giving the chromacities of the individual phosphors R, G, B plus the white point. The white point allows one to infer the relative brightness of the three phosphors, which isn't determined by their chromacities alone. Note that the absolute brightness of the monitor is not specified. For computer graphics works, we generally don't care very much about the absolute brightness levels. Instead of dealing with absolute XYZ values, in which X, Y, Z are expressed in physical units of radiated power, such as candelas per square meter. Candelas? Don't know what that is. I'll have to look that up. It is convenient to work with. I'm going to have to pause and look that up because it's distracting me, so I'll be back. Alright, quick aside. So, quick Google search. 1 candela per square meter equals 1 LUX. And we have a little article here on Wikipedia, candela per square meter. The candela per square meter symbol, CD divided by m to the power of 2, is the derived SI unit of luminance. The unit is based on the candela. And then there's some more information, so let's open up candela. Candela. The candela CD is the base unit of luminous intensity in the International System of Units. So the base unit of luminous intensity. That is luminous power per unit solid angle emitted by a point light source in a particular direction. Luminous intensity is analogous to radiant intensity, but instead of simply adding up the contributions of every wavelength of light in the source's spectrum, the contribution of each wavelength is weighted by the standard luminosity function, a model of the sensitivity of the human eye to different wavelengths. A common wax candle emits light in a luminous intensity of roughly 1 candela. Okay, so that's why they're calling it a candela, because a wax candle emits roughly 1 candela. Okay, so obviously there's a lot of information here, and maybe I'll read all of that later, but right now we just need enough to get a basic idea of what that was. So I'm just going to put this in my notes really quick and read that later, and we're going to get back to the article. I'm going to start from the top, though, since I kind of skipped around here. Okay, so note that the absolute brightness of a monitor is not specified. For computer graphics works, we generally don't care very much about absolute brightness levels, instead of dealing with absolute XYZ values, in which X, Y, Z are expressed in physical units of radiated power, such as candelas per square meter. It is convenient to work in relative XYZ units, where monitor's nominal white is taken to have a luminance Y of 1.0. Given this assumption, it's simple to compute XYZ coordinates for the monitor's white, red, green, and blue from their chromacity values. Why does CHRM use X, Y rather than XYZ? Simply because that is how manufacturers print the information on their spec sheets. Usually, the first thing a program will do is convert the CHRM chromacities into relative XYZ space. What can I do with it? If a PNG file has the gamma and CHRM chunks, the source RGB values can be converted to XYZ. This lets you bullet point, do accurate grayscale conversion, just use the Y component, bullet point convert to RGB for your own monitor, see the original colors, bullet point print the image in level 2 PostScript with better color fidelity than a RGB to CMY conversion could provide. Bullet point calculate an optimal color palette. Bullet point pass the image data to a color management system. Bullet point etc. End of page 92. On to page 93 of RFC-2083. How do I convert from source RGB to XYZ? How do I convert from source RGB to XYZ? Make a few simplifying assumptions first, like the monitor really is jet black with no input, and the guns don't interfere with one another. Then given that you know the CIE XYZ values for each of red, green, and blue for a particular monitor, you put them into a matrix M, and then M equals, and we have 3 columns and 3 rows, so it's a 3 by 3. Let's do it by column. I think column makes more sense. So XR, YR, ZR column. The next column is XG, YG, ZG column, and the next one after that is XB, YB, ZB column. So each column is a unique color, R, G, and B, and then each row is a unique letter, X, Y, and Z. So if you can kind of, so you're getting all of the different combinations of X, Y, and Z paired with X or Y or Z paired with G, R, or G or B, I think. Yeah? Because 3 times 3 is 9, yeah? Okay, yeah, I'm pretty sure. Anyways, let's keep going here. So we have this matrix with this 3 by 3 matrix that's combining RGB and XYZ. Here we assume we are working with linear RGB for floating point data in the range 0 to 1. If the gamma is not 1.0, make it so on the floating point data. Hold on. Here we are working with linear RGB floating point data in the range of 0 to 1. If the gamma is not 1.0, make it so on the floating point data. Then convert source RGB to XYZ by matrix multiplication. Okay, so now we got column vector XYZ, and that is equal to matrix RGB, and that's also just a column vector. In other words, x equals xr multiplied by r plus xg multiplied by g plus xb multiplied by b, and similarly for y and z. You can go the other way too. So the inverse calculation. So we have a column vector RGB equals IM. And this is, I think that's denoting a matrix. And then we have XYZ, which is a matrix or a column vector, where IM is the inverse of matrix M. Okay, so it's multiplied by inverse matrix, and then what is M up there? So M, okay, and M is, okay, so M is this transformation matrix, and so transformation matrix times RGB, so that first equation right up here, we got a transformation matrix multiplied by this RGB column vector gets you the XYZ column vector, a column vector just being a 3x1 matrix, right? Because it's the y-axis you mentioned first when you talk about the dimensions of a matrix. And so the inverse calculation, instead of M, you have inverse M. And inverse M multiplied by XYZ gets you RGB. So this is the inverse of this. So those are complementary equations. So where IM is the inverse of matrix M, okay? What is a gamut? The gamut of a device is the subset of visible colors which that device can display. It has nothing to do with gamma. The gamut of an RGB device can be visualized as a polyhedron in XYZ space. The vertices correspond to the device's black, blue, red, green, magenta, cyan, yellow, and white. Different devices have different gamuts. In other words, one device will be able to display certain colors, usually highly saturated ones, that other devices cannot. The gamut of a particular RGB device can be determined from its RGB chromatices and white point, the same values given in the CHRM chunk. The gamut of a color printer is more complex and can only be determined by measurement. However, printer gamuts are typically smaller than monitor gamuts, meaning that there can be many colors in a displayable image that cannot physically be printed. That kind of makes sense because monitors can emit light literally, whereas when you print something, you're using subtractive primaries, so they can't really create a literal glow. But that could be a horrible analogy. I'm not a color expert here. Okay, so end of page 93, on to page 94 of RFC-2083. Converting image data from one device to another generally results in gamut mismatches, -- colors that cannot be represented exactly on the destination device. The process of making the colors fit, which can range from a simple clip to an elaborated nonlinear scaling transformations, is termed gamut mapping. The aim is to produce a reasonable visual representation of the original image. Further reading. References. Color-1 through Color-5 provide more detail about color theory. And 15 appendix, sample CRC code. Okay, the following sample code represents a practical implementation of the CRC cyclic redundancy check employed in PNG chunks. See also ISO 3309, or ITU-T V-42, and then in square brackets, ITU-V42, for a formal specification. The sample code is in ANSI-C programming language. Non-C users may find it easier to read with these hints. Okay, so we have and, bitwise and the one that always confuses the hell out of me. Bitwise exclusive OR is a hat symbol, so what you might usually think of as a power symbol is a bitwise exclusive OR operator. Caution, elsewhere in this document, The hat symbol represents exponentation. Yes, so that one is the one that is going to get you. I write a lot of C, and I'm going to tell you that's the only one that confuses me, and I write a lot of C in JavaScript, and, I've done a lot of other languages. That's the only one that confuses me. C, JavaScript, Java, a little bit of C++. What else have I done? I've done, like, Visual Basic, some Mac script and Mel script and some Python. Yeah, this symbol right here, just make sure you pay attention to that. That's the only one that's really gonna get you, I think. Okay, but anyways, so when we have two, oh boy, shouldn't have done that. When we have two greater thans, that is bitwise right shift operator. When applied to an unsigned quantity, as here, right shift inserts zeros to the left, so it does a zero fill when it is an unsigned shift. Okay, and then we have the not symbol. There's another thing it's called. What is this called? Oh, exclamation mark. Yeah, so exclamation mark is a logical not operator, and we have a plus plus. And then within quotations, n plus plus increments the variable n. Then hexadecimal notation, 0x, n, n, n. 0x introduces a hexadecimal base 16 constant. Suffix L indicates a long value, at least 32 bits. So I don't see where that example with the L is, but L, maybe this is an old C code thing, but I don't see the suffix L used very much. Oh, wait, yes I do, for strings. Okay, so, and then a comment table of CRCs of all 8-bit messages, and then we have a line of code, unsigned long CRC underscore table, 256, so that's an array. And then a comment flag has the table been computed, initially false, int crc underscore table underscore computed equals 0, end of page 94, on to page 95. Make the table for a fast CRC, and then void make CRC table void. So it is a function that doesn't return anything and it doesn't take anything. Unsigned long C ints n and k. For n is going to be between 0 and 255 inclusive, going from 0 up to 255. C is a cast of n to unsigned long. We're going to have another loop nested within our n loop. This loop is k, and it goes from 0 to 7 inclusive, and that is going from incrementing from 0 to 7. If C masked with 1, so if the first bit of C is set, then C equals some ridiculous hexadecimal value, 0x EDB88320L to the power of, oh no, bitwise exclusive OR, god damn it, let me go back up. Bitwise exclusive OR. Yeah, so it's exclusive OR'd. Okay, so XOR'd. So, okay, so if the first bit of C is set, we're going to XOR, we're going to XOR, and we're going to use this first hexadecimal value, 0x EDB88320L. We're going to XOR it with C bit shifted 1 to the right. Otherwise, C is just C bit shifted to the right without any XORing. And CRC table n equals C, so we're going to make an entry at the end of the, what loop are we in here? At the end of the n loop, we're going to make an entry. And then at the outside of the end loop, so outside of the loop, rather than the rather than the last operation before the next iteration of the end loop, outside of the end loop, we're going to do CRC table computed equals 1. So we're just going to flag that we have done the computation. And then a closing brace on the function. Update a running CRC with the bytes buff 0 to len -1 dash dash. The CRC should be initialized to all ones, and then transmitted value is the ones complement of the final running CRC. See the CRC routine below. Okay, so unsigned long update CRC. It takes 3 parameters, and those parameters are CRC, buffer, and length. It's unsigned long CRC, unsigned char, pointer buff, and integer length. We're going to open up the function with the open curly brace. Unsigned long equals CRC, declare int n. If not CRC table computed, make CRC table. For n equals 0 to less than length, so we're going to go through every entry in an array, and the array is the buffer, okay? And C equals CRC table, and we're going to open up our array accessor and put in C XORed with buff n masked with 0xFF, and that will be the indexer within CRC table. And we're going to XOR that with C bit shifted over to 8, and that gives us the value C. And I cannot comprehend exactly what that is doing. I'm just stating what it's doing. So don't act like I'm a genius or anything here. I don't know. I'd have to do more research. And then return C, and then close the function off. All right. Return the CRC of the bytes buff to length -1, unsigned long CRC, and it's going to take 2 parameters, the buffer and the length, unsigned char pointer buff and integer length. Open the function, return update CRC, and it is all the bits set in what looks like a 32-bit integer. Well, this denotes 32 bits, and also what I see here is 32 bits. So we have, let's just do R, G, B, A. It doesn't have to be R, G, B, and A. That's just the way I count when I'm counting bytes, just because, I don't know, that's just the way I conceptualize it. But there's 4 bytes there, therefore 32 bits. So yes, this is just 32 set bits. The buffer and the length are given to the update CRC function, and then we are going to XOR it with a mask that is all 32 set bits, and I believe that would just flip the bits, because XOR will only return a 1 if one or the other is set. And if we're going to XOR it with something that already has all 1s, then a 0 and a 1 will give you a 0, so that'll flip it. And then a 1 and a 1 will also give you a 0, and that'll flip it. A 1 and a 1 will give you a 0, so that'll flip it. Okay, yeah. So XORing with just all set bits, that is just going to take whatever you got from here. It's just going to invert the bits. It's just going to toggle every single bit and just flip it to the inverse. So if the bit in here is a 0, it's going to turn it to 1, and if it's a 1, it's going to turn it to a 0. So that's what the effect of XORing with a bit mask that is all set bits is going to do here. Okay, so we are on the end of page 95, and we are now on page 96 of RFC-2083. Okay, so 16 Appendix Online Resources. This appendix is not part of the formal PNG specification. This appendix gives the locations of some internet resources for PNG software developers. By the nature of the internet, this list is incomplete and subject to change. And since this was written in 1997, oh yeah, it's but, it could give us some hints at where to go, so I'm going to read it anyways. Archive sites. The latest released versions of this document and related information can always be found at the PNG FTP archive site, ftp://ftp.uu.net/graphics/png. The PNG specification is available in several formats, including HTML, plain text, and PostScript. Reference implementation and test images. A reference implementation is Portable C is available from PNG FTP archive site, ftp://ftp.uvu.net/graphics/png/source. The reference implementation is freely usable in all applications, including commercial applications. Test images are available from ftp://ftp.uu.net/graphics/png/images. Electronic mail. I think they mean email, but this is an old document. Electronic mail. The maintainers of PNG specification can be contacted by email at png-info@uu.net.uu.net or at pnggroup@w3.org. PNG Home. There is a World Wide Web homepage for PNG at http://quest.jpl.nasa.gov/png. This page is a central location for current information about PNG and PNG-related tools. 17. Appendix Revision History. This appendix is not part of the formal PNG specification. The PNG format has been frozen since the 9th draft of March 7, 1995. All future changes are intended to be backwards compatible. The revisions since the 9th draft are simply clarifications, improvements in presentation, and additions of supporting material. On 1 October 1996, the PNG specification was approved as a W3C World Wide Web Consortium recommendation. End of page 96. Page 97 of RFC-2083. Changes since the 10th draft of 5th of May 1995. Bullet point, clarifying meaning of a suggested palette PLT chunk in a true color image that uses transparency. Bullet point, clarified exact semantics of S-bit and allowed sample depth scaling procedures. Bullet point, clarified status of spaces in TEXT chunk keywords. Bullet point, distinguished private and public extension values in type and method fields. Bullet point, added a creation time TEXT keyword. Bullet point, Macintosh representation of PNG specified. Bullet point, added discussion of security issues. Bullet point, added more extensive discussion of gamma and chromacity handling, including tutorial appendices. Bullet point, clarified terminology, notably sample depth versus bit depth. Bullet point, added glossary. Bullet point, editing and reformatting. 18. References. So within the square brackets, color-1, Hall, Roy, Illumination and Color in Computer-Generated Imagery, Springer-Verlag, New York, 1989, ISBN 0-387-96774-5. Color 2, Casson, J, and W, I can't pronounce that, PLOUFFE, An Analysis of Selected Computer Interchange Color Spaces, ACM Transactions on Graphics, Volume 11, Number 4, 1992, pp. 373 to 405, so I'm guessing those are the pages, and I don't know what PP means, maybe paper pages, I don't know. Color 3, Lily C., F. Lynn, W.T. Hewitt, and T.L.J. Howard. Color in Computer Graphics, CVCP, Sheffield, 1993, ISBN 1-85889-022-5, also available from URL http://info.mcc.ac.uk/cul/color COLOUR_announced.html. And then we have color 4, Stone, MC, WB, Coan, and JCBD, color gamut mapping and the printing of digital images, ACM transactions on graphics, volume 7, number 3, 1988, pages 249 to 292, and no ISBN on this one, so I'm going to just say this again since there's no ISBN in case you want to look it up. So stone, m.c. w.b.cowan, and j.c.beatty, and within quotations, color gamut mapping and the printing of digital images, and then close quotations, ACM transactions on graphics, volume 7, NO3, within parentheses 1988, pp 249-292, and then a period. Okay, so now on to color 5. So color -5 within square brackets, Travis David, effective color displays, Theory and Practice, Academic Press, London, 1991, ISBN 0-12-697690-2. Then we have Gamma FAQ, Poynton, Poynton, C. Gamma FAQ. There's the URL, http://www.info.ramp.net/ and there's some escape sequences in here. So /%7e POYNTON -COLOUR.html. And that is the end of page 97. On to page 98 of RFC 2083. We have, within square brackets, ISO-3309, International Organization for Standardization, Informational Processing Systems, Data Communication, High-Level Data Link Control Procedure, Frame Structure, IS-3309, October 1984, 3rd edition. Then we have ISO 8859, International Organization for Standardization, Information Processing, 8-bit signal byte coded graphic character sets, Part 1, Latin alphabet number 1, IS-8859-1, 1987. Also see sample files at ftp://ftp.uu.net/graphics/png documents /ISO_8859-1. And then there's a **, don't know why, ITU-BT709. International Telecommunications Union, basic parameter values for the HDTV standard for the studio and for international program exchange. ITU-R recommendation BT.709, formerly CCIR Rec. 709, 1990. Within square brackets, we have ITU-V42, International Telecommunications Union, error correcting procedures for DCES using asynchronous to synchronous conversion, ITU-T recommendation V.42, 1994, revision 1. Within square brackets, we have PAETH, or PAETH, I don't know, PAETH, PAETH, A.W, image file compression made easy. In Graphics Gems 2, James Arvo, editor, Academic Press, San Diego, 1991, ISBN 0-12-064480-0. And then we have PostScript within square brackets. Adobe Systems Incorporated PostScript Language Reference Manual, 2nd edition, Addison Wesley, reading 1990, ISBN 0-201-18127-4. We have PNG extensions within square brackets, PNG group, PNG special purpose public chunks available in several formats from ftp://ftp.uu.net/graphics/png/documents/png extensions.star. Within square brackets, RFC-2083, Brandon, R. Editor, requirements for internet hosts, applications and support, STD3, RFC-1123, USC Information Sciences Institute, October 1989. The URL, ftp://ds.internetnet/rfc/rfc1123.txt. End of page 98, on to page 97 of RFC 2083. Within square brackets, RFC-2045, Fried N. and N. Borenstein, Multi-Purpose Internet Mail Extensions, MIME Part 1 Format and Internet Message Bodies, RFC 2045, Inusoft, First Virtual, November 1996, URL ftp://ds.internnic.net/rfc/rfc2045.txt. RFC 2048, Fried N. I can't pronounce that. KLENSIN, J and J Boutell, Multi-Purpose Internet Mail Extensions, MIME Part 4, Registration Procedures, RFC 2048, Inusoft, MCI, USC/Information Sciences Institute, November 1996. The URL ftp://ds.internetnet/rfc/rfc2048.txt. RFC 1950, Deutsch P and JL Gailey, zlib compressed data format specification version 3.3, RFC 1950s, Aladdin Enterprises, May 1996, URL ftp://ds.internnic.net/rfc/rfc1950.txt. Whew, okay, and then we have RFC 1951 within square brackets, and this is coming directly after RFC 1950. So RFC 1951 in square brackets is Deutsch P deflate compressed data format specification version 1.3, RFC 1951, Aladdin Enterprises, May 1996. URL ftp://ds.internnic.net/rfc/rfc1951.txt. Next, we have within square brackets SMPTE-170M, Society of Motion Picture and Television Engineers, Television Composite Analog Video Signal NTSC for studio applications. SMPTE-170M 1994. End of page 99. On to page 100 of RFC 2083. We have section 19, credits, editor, Thomas Boutell. Boutell, oh boy, I just went a little bit recursive there. Editor, Thomas Boutell, and that is boutell@boutell.com. Contributing editor, Tom Lane, TGL @sss.pgh.pa.us. And we have some authors. Authors' names are presented in alphabetical order. So we got Mark Madler @alumni.caltech.edu, Thomas Boutell@boutell.com, Christian Brunchin, cb@df.lth.se, Adam M. Costello, amc@cs.berkeley.edu, Lee Daniel Crocker, lee@piclab.com, Andreas Dillinger, adillinger@enel.ucalgary.ca, Oliver Fromm at rz.tu-claushal.de, Jean-Luc Begali, gzip at prep.ai.mit.edu, Chris Herborth, and that's CHRISH at QNX.com, Alex Jacquelin, ALEKS.JAKULIN at snet.fri.uni-lj.si, Neil Kettler at cs.colostate.edu, Tom Lane, TGL at sss.pgh.pa.us. We got Alexander Lehman, maybe? Alex at hal.rhein-main at DE. I'm just butchering these names. Chris Lilly, Chris at w3.org, Dave Martindale, Dave M at cs.ubc.ca, OWEN MORTENSEN, interesting, 104707.650 at CompuServe.com, Keith S. Pickens, KSP at swri.edu, Robert P. Poole, Lionboy at primenet.com, Glenn Randers Fierson, and Glenn RP at arl.mil, or RANDEG at alumni.rpi.edu. Greg Rolofs, Newt at pobox.com, William Van SCHAIK, William at gintic.gov.sg. And then no email for this guy, Guy, SCHALNAT, Paul Schmidt, PSCHMIDT at PHOTODEX.com, Tim Wegner, 71320.675 at CompuServe.com, Jeremy Wool, Jeremy W at Anders.com. Okay, then we have the authors wish to acknowledge the contributions of the Portable Network Graphics mailing list, the readers of comp.graphics, and the members of the World Wide Web Consortium, W3C. End of page 100. Page 101, RFC-2083. The Atom 7 interlacing scheme is not patented, and it is not the intention of the originator of that scheme to patent it. The scheme may be freely used by all PNG implementations. The name Atom 7 may be freely used to describe the interlace method 1 of the PNG specification. Trademarks. GIF is a service mark of the CompuServe Incorporated. IBM PC is a trademark of International Business Machines Corporation. Macintosh is a trademark of Apple Computer Incorporated. Microsoft and MS-DOS are trademarks of Microsoft Corporation. Photo CD is a trademark of Eastman Kodak Company. PostScript and TIFF are trademarks of Adobe Systems Incorporated. ASCII is a trademark of Silicon Graphics Incorporated. X-Window System is a trademark of the Massachusetts Institute of Technology. Copyright notice. Copyright 1996 by Massachusetts Institute of Technology, MIT. This W3 specification is being provided by the copyright holders under the following license. By obtaining, using, and/or copying this specification, you agree that you have read, understood, and will comply with the following terms and conditions. Permission to use, copy, and distribute this specification for any purpose and without fee or royalty is hereby granted, provided that the full text of this notice appears in all copies of the specification or portions thereof, including modifications that you make. This specification is provided as is, and copyright holders make no representations or warranties expressed or implied by way of example, but not limitation. Copyright holders make no representations or warranties of merchantability or fitness for any particular purpose, or that the use of the specification will not infringe any third-party patents, copyrights, trademarks, or other rights. Copyright holders will bear no liability for any use of this specification. End of page 101. Page 102 of RFC 2083. The name and trademarks of copyright holders may not be used in advertising or publicity pertaining to the specification without specific written prior permission. Title to copyright in the specification and any associated document will at all times remain with copyright holders. Security considerations. Security issues are discussed in security considerations, section 8.5. Then we got authors' addresses. Well, we already see the first one, so let's see, authors' addresses. So we got Thomas Boutell, P.O. Box 20837, Seattle, Washington. We got a phone, 206-329-4969. Email, boutell@boutell.com. Not sure if that counts as doxing, but it is public, so, and that's also a P.O. box, so I'm going to guess those are not home phone numbers, but some type of professional contacting numbers. And that is the end of RFC 2083. So that's the last page is page 102. So we are done with RFC 2083. And yeah,